In the intricate world of data management, envisioning the flow of information as an oil pipeline offers a vivid analogy. Just as oil must be carefully extracted, transported, and refined, data too requires meticulous processes to ensure its value is maximized. This course serves as a blueprint for constructing and optimizing your data pipeline, comparing the strengths and functionalities of data proc, data prep, data flow, and data fusion. In this course, I'll talk through the realms of big data processing, starting with the exploration of data proc cluster options, followed by hands-on experience in creating a data proc cluster and running a Spark job. Dive into the transformative world of data prep flows, mastering the art of profiling, transforming, and sampling data. I'll then shift focus to data flow, where you'll learn to build and deploy robust data flow pipelines and understanding the various options to fine-tune their performance. In the segment on data fusion, I'll give insights into setup and management, culminating in the creation of a data fusion pipeline. Finally, I'll conclude with a critical analysis of the pricing models for data proc, data prep, and data flow, empowering you with the knowledge to make cost-effective decisions in the data-driven landscape. This course is one of a collection that prepares learners for the Google Professional Data Engineer exam.
In this video, I'm going to describe the key differences between services that are part of managing the controlled inflow of data. So in Google Cloud, we have one service that's known as Google Data Proc. Data Proc is a fully managed and completely scalable service that's great for running things like Hadoop, Apache Spark, Flink, Presto, and over 30 different open source tools and frameworks. We use Data Proc for data lake modernization, and we use it for ETL or extract, transform, and load processes, and it's also great for secure data science at scale. Now, this can be integrated with our Google Cloud at a fraction of the cost, and it can be open and run with open source data analytics at scale with enterprise-grade security. That's the advantage of using Data Proc. We also have Google Data Prep by Trifacta. Now, what Data Prep by Trifacta is just a Google Cloud's intelligent data service for allowing us to explore our data visually. It allows us to clean and prepare diverse data sets for analytics and machine learning. And this is where the true power of Trifacta comes in, is that it allows us to do this kind of data analysis and data exploration with our tool here that is great for machine learning. So I can take this data that's cleaned with Trifacta and prepare it for a machine learning use case. And you want to also look at is known as data flow. Google Data Flow is another service. This allows us to unify, stream, and batch data processing, and it's totally serverless, and it's fast and cost effective. This is where the serverless comes in very useful here, is that we don't actually have to manage any infrastructure on our own. We use Data Flow to actually do this batch processing for us, and Google is going to then spin up the required infrastructure for us on demand as we need it for the services that we're using. This is where we have things like automatic provisioning and management. And so it's great for managing our processing resources, which could be a wide variety of services such as virtual machines or hardware in Google infrastructure. You'll also get some real-time insights and activation, as well as having horizontal and vertical autoscaling of all of our worker resources to maximize resource utilization. And this is where we will get the use case out of data flow. And then a couple more that I want to discuss here is data fusion. Google Data Fusion is really powerful. This is another fully managed cloud-native data integration tool that's used for at any scale, either small data or big data. It is a codeless deployment of ELTs or ETL pipelines, so it's very low code. And there's more than 150 pre-configured connectors and transformations that we can use here. Similarities and differences between these services can seem a little terse at first, but I'll try and make this as digestible as possible. So here we've got our Data Proc. So it's a managed Hadoop system. It is requiring some coding, so some engineering is required here. And there is a pipeline migration that's also offered. In Data Prep, This is actually the cloud storage, BigQuery, Dataflow, and Looker integration is built into DataPrep. And this is codeless, meaning that it's very low code. You can actually do this in a GUI and set up your pipelines this way. And it's great for pipeline execution for our tools. We also have things like Dataflow, which includes things such as Apache Beam support, as well as requires some type of engineering know-how because it will require some coding. It's not low code like we see with DataPrep. And it is allowing us to create new pipelines this way, and then we can execute them with another tool. Data Fusion is another one that is there. We have Cask Data Application Platform, and this is where the tool comes in very useful, but it's also codeless. So it's great for doing things like data engineering with a very low code use case. So not a lot of engineering is required. You don't actually have to know how to actually program in this case. Again, DataPrep and Data Fusion is very useful for when you're doing something in a GUI. So you can actually use the console itself to set up these pipelines for yourself. And Dataproc and Dataflow, again, they used a little more advanced features, so they require a little more coding. And they're great for things like creating new pipelines and pipeline migration at a granular level without having to rely on Google Cloud Console for any way. And that is a little bit on how we can use these kind of tools. So we use things like Dataproc, Dataprep, and Dataflow and Data Fusion, and they each have the pros and cons for what we're trying to use them for. In this video, I'm going to identify some of the options that are used to optimize Dataproc for different situations. So when we're working with Dataproc, what you'll notice is that there's going to be some open source components that are installed on Dataproc clusters, and they contain many different configuration files. For example, we have Apache Hadoop, Yarn, Hadoop Distributed File System, HDFS, and we have Spark. And each of these have several XML and plain text solutions for us. And so what this means is that we can use the properties flag on our command line tools, such as gcloud dataproc clusters create command, to modify many of these common configuration files when we're creating a cluster. And there's certain formats that we want to make sure that we're using. So typically what's going to happen is we're going to provide a list of these settings and properties with the -- properties flag, and it's going to accept things in a string format. So we'll have things such as a file, its prefix, and then a colon, and then a property name in that file, and then an equal sign and the value for that property. And then followed by a comma, and we give it another file name, a file with its prefix, and a colon, and another property, and set an equal sign and its value for that property. And you do that for everything here. The file prefix that I'm talking about here is just going to map to a predefined configuration file that is going to be used for whatever service that you're trying to modify, whether that's Apache Hadoop, or you can use Yarn, or a distributed file system, or Spark, whatever it might be, whatever service that they have, you can use the -- properties flag to modify it. And there's different service properties that we can have, and you can look through what these services and what their properties are contained on the Dataproc cluster directly in the cloud documentation in the Google Dataproc documentation on Google Cloud. And you can see a list of all of these services that you can modify. Now there's different regional endpoints. So what this means is that it's going to work off of the compute engine regions. And so I can specify a region such as US East 1 or Europe East 1 when I create a Dataproc cluster. And what Dataproc is going to do is it's going to isolate those cluster resources. That could be a VM instances or a cloud storage bucket and metadata storage within a zone within that specified region. And you can follow the semantics here for regional endpoints. So when we're looking at a region, if I'm looking at the US region, central US region, I'm going to give it US-central 1. That's the semantics that follows. And the name of the Western Europe region is Europe-West 1. And I can run the gcloud compute regions list command to see a list of available regions in the CLI. And that's how we can modify everything there. Now the cluster creation we have to specify a region using the required -- region flag when we're using the gcloud command line tool. So I'll be using the gcloud dataproc clusters create, followed by a cluster name, followed by -- region equals, and the name of the region and any other arguments that I want to use. And that's typically how it's done through the command line. You can also do this through the console itself, where we'll ask you for the region and you can just type it in there. Now, auto zone placement, when we created Dataproc clusters, cluster resources are going to use a regional endpoint based on the compute engine zones. When I'm choosing a region, I have to select a zone within that region, or I can omit the zone to have Dataproc use what's known as an auto zone feature. Selecting a zone for us in the region is what this purpose of the auto zone placement will do. So if I don't know what zone I want to use within the region, I just know that I want my Dataproc cluster to be in US Central 1 or US West 1 or whatever it might be. What'll happen here is that each region has a couple of zones at least, and I can have Dataproc select the zone based on my requirements that I'm using. And what'll happen here is that once a zone is selected, all nodes for that cluster will be deployed to that zone, and auto zone and resource reservations is going to be implemented. It's going to just follow based on what criteria I need my cluster to have. So if a cluster creation requests 20 CPUs, and AutoZone will prioritize certain zones for selection according to the total number of CPU reservations available in that zone. And so it'll just figure out which zone is the best one for the requirements that I've specified for my cluster. And that's pretty much how this AutoZone placement will work. Now, initialization actions are important because when we're setting up a Dataproc cluster, what I can do is I can specify initialization actions. And what these are they're basically just scripts that are executed on all nodes as the cluster is created. And what these actions will prepare the cluster for specific jobs by installing necessary dependencies. And it's recommended to store these scripts in a personal cloud storage bucket for stability and not rely on the public Google hosted script repositories for production environments. I usually typically have these in a GitHub repository as well. And those are just some key considerations that you want to think of when you're trying to put these type of custom initialization actions somewhere. And the usage for these things just can be done directly through the console, or you can actually use a command line, the Google Cloud command line tool, to actually run these initialization scripts as you create your cluster. So I use the gcloud dataproc cluster creation command, followed by a -- initialization -actions. That's the name of the flag, and then set it equal to a cloud storage, or I can use my GitHub code to retrieve it and run that information for me. Logging is important too. So when I'm working with logging, output from the execution of each initialization action is going to be logged for each instance in a certain location. And that is going to be dependent on what tools I've used, what properties I've used in the command line tool. So I can actually have it run by default and store all logs in a location instance on my cluster, such as var log dataproc-initialization-script-x.log, where x is the zero-based index of each successive initialization action script. So that means that x would be the order. So 0 would be the first script that was run, and then 1 would be the second script, and 2 would be the third script, and so on and so forth. And that's really where these logs are going to live. So as these initialization scripts are running, they're going to be printing things to the console or whatever. We can actually have these things logged directly to file. That file is going to store there, so I can actually have them there for troubleshooting purposes if I need them. Now, there's also flexible virtual machines that I want to talk about. So we've got things like, why use a flexible virtual machine? Well, what's the difference between a flexible one and a non-flexible one? So if a VM type was unavailable when you submitted a cluster creation request, what'll happen here is the request will fail, and you need to update your request, your script, your code, and to specify what's known as a next best VM type. So in a perfect world, I would need this VM type, but if it's not available, I'll take this one. So this re-request process could involve multiple iterations until you specified a VM type that was available. Instead, what's going to happen here with the flexible virtual machine is Dataproc is going to help us select, okay, not our first choice isn't available, we'll go to the second choice. If the second choice is not available, we'll go to a third choice. That's the idea of making it flexible. So it helps us during our cluster creation requests so that we have a secondary worker VM type from our ranked VM list. So we give it, this is what I want first. If that's not available, I want this VM type or this VM type or this VM type, and I give it. It's going to start searching for zones within my specified cluster region with availability of all the listed VM types. And so that's the purpose of it. So some key terminology I'll bring up here is when I talk about a VM type, I'm talking about the family of virtual machines, the memory capacity, the number of CPU cores for a VM instance. All of these things tell me what I want to use. And so Dataproc is going to support the use of what's known as predefined and custom virtual machine types that I give. You'll also see things known as secondary workers. Secondary workers means that they're not storing any data. What they're doing here is that they're functioning only as processing nodes. You use secondary workers to scale compute without scaling the storage. So you don't need to, they're not meant to store anything, they're just meant to process things quick. Let's go into key considerations here as well. So the limitations and considerations that I'd want to talk about here is that flexible virtual machines are available in Dataproc on compute engines of 2.074 or 2.1.22 and up, and later Dataproc on compute engine, and there's different image versions that are available. And you'll notice here is that you're going to have to request virtual flexible machines. So that is going to be important. So you can specify up to 5 ranked VM type lists with up to 10 VM types in a list. And so you can have a lot of different virtual machines ranked, and then Dataproc is going to choose the best one for you and for your use case automatically. Next thing I'll give here is that there's scheduled deletion of clusters. So it's important that we want to avoid incurring charges in an active cluster. So what we want to do is we want to implement what's known as scheduled deletion. So after a specified cluster is idle for a certain period of time, we can turn it off there. We can have it set to so that at a specified future time, at this date, at this time, we can delete the cluster. After a specified period that starts from the time of submission of the cluster creation request, we can also delete the cluster there. And so you can actually view your scheduled deletion settings there, and you can take a look at what settings are available for this cluster that you have directly in the console or through the command line tool. And you can modify these deletion settings at will there. But what's important is that you do have them in place at least for after a cluster is idle for a certain period of time and it's there and incurring costs. You don't need it there. You can actually turn it off completely. So what Dataproc will do is it'll automatically delete the cluster for you, at which case you can use your script or some type of Terraform script to bring it up the cluster if you need it again. And that's the idea of actually trying to save us costs. It's because these things can be very expensive and you can actually incur a lot of costs, especially depending on how many virtual machines are in this cluster. So that is a little bit on how Dataproc works and some of the services that are available within a Dataproc cluster.
In this video, I'm going to show you how we can actually build and create a cluster in Dataproc. So first, to get started, we are going to start at the Google Cloud Console at the very top there, and we are going to go up to our search and search for Dataproc. The Data, P-R-O-C, all one word. And we're going to get here to where it says Dataproc Managed Apache Hadoop. We're going to go ahead and click this one. And what first you'll actually see on the page is asking you to enable any API. If this is the first time you've been on the Dataproc service, it'll make sure to enable the API for your account so that you can be billed. After you've done that, it should take a couple of minutes for you to get to this screen where you'll see something that looks like this, where there are no clusters available. So you're going to create a cluster by clicking Create Cluster up at the top left, and you'll see this little modal will pop up. Now there's two options to select infrastructure service that we want to use to actually create our cluster. We can use a Google Kubernetes engine, or we can use the compute engine. The Google Kubernetes engine works with autoscaling for horizontal scaling, and it'll be able to add nodes to the cluster as traffic increases and be able to take away nodes from the cluster when traffic decreases. So this is a little more flexible. For our purpose, we're just going to worry about creating one on the compute engine. So we're going to click Create here next to the compute engine, and then we're going to be asked to fill in some forms and some configurations that we can do. First thing we're going to do is we're going to give it a cluster name. So I'm just going to call it Data, my-data proc cluster. You can call it anything you'd like, but for now, since this is just an example, I'll leave it like so. I'll choose the region, such as US Central 1, and use any zone here, which is any. And then scroll down, you can see here that there's different types. of versioning that we can use. So I'm using 2.2 Debian 12. I can change that to another operating system if I choose to. For now, that should be more than enough. And then I can also enable some Spark performance enhancements. So let me just talk a little bit about the cluster type before I go on to the other ends. So there's different types of cluster types that I can create. So there's high availability, which is the 3 master nodes and worker nodes that I choose how many worker nodes are going to be attached to the cluster. And so this is going to provide uninterrupted yarn and HDFS operations, even if you have single node failures or reboots. I can have a single node with 0 workers. So this is just providing one node that acts as both a master and a worker. And this is good for our proof of concept or small scale processing. And standard is just your standard. This is normally what you'll be using. This is going to have one master node, which is going to talk to n worker nodes that are actually doing the work. So we actually submit jobs to the master node. The master node will split those jobs accordingly to the n worker nodes and send them over. So that's actually what's being done here at the standard scale. So we can also do a single node if we choose to for our proof of concepts. For now, I think this is enough for what we're trying to do. So I'll actually choose single node. And I'll scroll down a little bit. And what will happen here is that we're going to create some Spark performance enhancements, so enable advanced optimizations. There's different advanced execution layers, or even Google Cloud Storage caching if we want those output files to be sent over to Google Cloud Storage. This is where we'd go. There's different auto-scaling features that are available as well, and some network configurations that we can actually handle. So I will actually use the default networks in this project. So that's just kind of where this is going to be housed and what VPC. So that's perfectly fine. You can just leave everything as the default there. And then there's different metastores or components that I can use. And that's pretty much how we can work with this. Now, these metastores, these are basically where we'd have different metastore services that are attached to our Hive. If you're using Hive in this cluster, in this case, we don't actually need anything from the metastore, so we can just leave it as blank. Most of this stuff really becomes specific to your use case that you're trying to work with. In our example here, we're just using it as a simple proof of concept just to see if it'll work. And then that's the idea of using a single node, picking a region, any zone, it doesn't matter. And then you should be good to go. Now, the next step is to configure our nodes, which are optional. And this is where we get to actually configure how many nodes there are and what CPU and GPU platform that they're going to use. So you can see here that we've got, this N2 series, N2 standard 4. So I'll have 4 virtual CPUs and 3.75 gigs of memory. I can also start to use a SSD if I want to. In this case, I'm just going to use a primary disk, which is just a balanced persistent disk of 500 gigs. And I can edit that for whatever I'd like. And then I can have things like sole tenancy, which enables the cluster and sole tenant nodes. It makes sure that I have exclusive access to the actual physical hardware that the compute engine server is dedicated to hosting. Right now, what will happen is that the system here is going to be sharing the hardware with other tenants that are trying to use Dataproc. So you may, depending on your security, you may need to enable this or disable it. It'll cost more if you do enable it because you're actually getting the whole hardware dedicated to you. It may be important for your use case. It may not be. That's for you to decide. But that's really what this does. Okay, so that's a little bit on how these nodes are going to be configured. You can even customize the cluster itself by adding different labels and properties. And from then on, you can have a scheduled deletion so that this is important after it's idle for a period of time. So I can have delete after a cluster idle time without submitted jobs. So if the cluster is just spun up for 2 hours and nothing's being done, to save cost, I can just delete it because remember, you are going to be charged on a per hourly basis as this hardware is spun up for you. So that's important. And then we have a staging bucket that is useful. So this is where we can actually store our job dependencies, our driver output, and cluster config files. And that should be fine for that. So make sure you choose a storage staging bucket for this. After all of this is done, you can move over to the managed security. So this is where we can use either our own supplied key, or we can actually use Google's keys that are owned by Google. Depending on your security compliance that you're trying to follow, you may have to use your own. But for now, I'll just leave it as Google Cloud managed. And then if I scroll down, there's different things here that are just disabled by default. So such as personal cluster authentication to allow interactive workloads on the cluster. I may have to enable this. But again, these are more specific security features that are attached to Dataproc cluster that may or may not affect us, depending on your use case. I've always left these as disabled. There could be times where I would have to enable them, but that's usually just to deal with your cybersecurity team telling you we're going to need these features turned on for security compliance. So after all of this is done, I can just click Create, and then my cluster will start to create. It should take about 30 to 45 minutes to spin everything up. I can also use the equivalent command line tool. So this would be the CLI command that I would run on my console. So this is how I can use code to actually create the same cluster that I've created in here. And that's pretty much it. That's how we can actually create a Dataproc cluster on Google Cloud.
In this video, I'm going to describe the purpose and basic configuration options of Data Prep Flow. So let's talk about Cloud Data Prep. What Cloud Data Prep is just a way for us to use it as a data preparation web application tool that's in the Google Cloud platform. And this has been used for a while. It's not new. The tool is very useful for data analysts and data scientists primarily. They're used to visually explore, clean, and transform a data set. And it's done using a very simple workflow of drag and drop transformations in a user-friendly low-code interface. And it's very quick for the analysts and the data scientists to get some insights into the data. So how this works, it has a container for holding the objects. So you create an end-to-end data pipeline, and we use these things called flows. And these flows can perform a following type of actions that I'll talk about here. One of them is that it allows us to combine data sets by performing union or join functions. It allows us to use share flows with other users. So it creates output definitions and generate job results for them. And that's very useful for this. And it can also handle scheduling the execution of our jobs, as well as working with references between recipes and external flows. So recipes are the drag and drop step-by-step instructions so that we can explore, clean, and transform a data set. So we can actually create references between our recipes in these external flows. And it also allows us to export and import into different instances of data prep. And so this is the idea of what data prep does with flows. Let's talk a little bit about flow view. Now, in flow view, what this means is that we can create the objects that are part of a flow. So for example, we'll have a top bar. So from the top bar of a flow view, I can access a variety of options to perform some functions. So I can share a flow, add data sets to a flow. I can even search the flow for objects that is inside of my flow. So anything that is useful for transforming our data set, there'll be some object there. And so the top bar will allow me to do those kind of search and share functionality. A flow canvas is the primary workspace for our flow view. This is where we're going to add new objects and organize them. I can add recipes for imported data sets. I can add an output for a recipe. I can add more imported data sets. There's even a place for me to auto-arrange my icons that are in my flow canvas. I can even zoom in the canvas and I can add notes just like I can with comments on code. And I can also have something known as a context panel. So when I select an object in the flow, I can find additional options in the right panel. And this is where the context panel will contain things. And the available options will depend on the type of object that we selected within the flow canvas. But this is where the idea of what a flow view will do. Got a top bar for searching and sharing, a flow canvas for actually placing our objects and our recipes that we're looking to work with, and a context panel. So when we click on a recipe or an object, there will be some settings for that recipe or object over on the side. That's the general features. Let's talk a little bit about some flow features. So, flow objects can exist, right? So there are some required objects. So required flow objects, we want them to create an end-to-end data pipeline. I have to make sure that there's certain objects that I need to have. One of them is obviously I need to have an imported data set object. obviously, this is the first object that's going to be used to import data set from an external source. And this could be a reference to a file or a table-based source of data. And then the next thing I'm going to need is a recipe. And this is a set of steps to transform our data after I receive the import. This is kind of our transformation layer. And our output is a definition for the type, the location, and the format of the results generated by our recipe, and some additional settings. And that's really the required objects here that we need. So the first thing I want to discuss just in detail is what an imported data set is. So I kind of mentioned it earlier. It's just a reference to a data set that you can import some data into. So I can import data sets from a variety of flat file formats or distributed data distribution systems, such as a database, for example. And an imported data set could be multiple files, a single file, a database table. It could be any type of data at all. But this is basically going to act as our source. The recipes now is just a series of user-defined transformation steps that can be applied to our data. This is where you might, start doing some type of data cleaning, some data processing in this step, and you'd use these recipes for them. So I can create a recipe from an imported data set, and the steps in this recipe are then applied to that data. And I can even create a recipe for another recipe to join recipes together. So it's not just one. I can have maybe a recipe to remove duplicated data in the data set. I could have another one to do some data imputation. Many different things that I could do. And each recipe could be linked together. So the output from one recipe will be input for another, and so on and so forth until we've actually finished the entire transformation layer and we're ready to load our data. So here are some flow features that, again, I want to talk about. So this is the output layer. So an output will just define the set of files, tables, formats, and locations where the results of the recipe's transformations are written after the whole job has been run and completed. So I'm going to need a publishing action to do this. And this is going to define how the results are written. Again, location, format, and just some format-specific settings that matter. Now, search flows, you can actually search for specific objects in our flow, and they help to filter complex flows. So when I start typing a search term, search results are highlighted in yellow, for example, and you'll see it actually in the Google Cloud. And so this allows me to actually do some searching for objects that are in my flow canvas, and that's where this is used there. Okay, so some more flow features that I want to discuss, and that's the concept of sharing our flows. So flow sharing allows us to, with other users in our project or workspace, I can actually just share the whole flow for someone else to use. And this is where someone can actually go ahead and run that flow in their own instance. I can even organize my flows into folders, and a folder is just a container for storing all of the flows that I may have. So from the flows page, I can just create a folder, and then it's a way just for me to organize all the flows. Think of each flow as a single file inside that folder. Each flow, each file in that folder has a certain job or some type of ETL that can be done on a source of data. And you may want to share that specific file or specific flow with somebody else in your user, and you can actually do all of that. Now, working with flows, is not very difficult. The first thing is we have to create the flow. And so this is where we're going to need things like creating a name of a flow. We can actually connect some data to that flow and then import that data set by selecting the appropriate source. And then I can actually have some type of step to do some transformation. And this is where we want to be able to apply our recipes. Now, what this means is that I'm going to actually be doing some type of data transformations. Now, if I take some data, I'm going to create some recipes. And so the recipes could be data cleaning, like changing the name of columns, changing the data type of a column, removing duplicates. I can also do things like data discovery for filtering data according to a specified condition. And there's even data enrichment policies that can be done. I can then, once I have everything ready to go and I've got my flow all designed, I now just need to run the data flow. And this is where you literally just click run in the Google console. And it'll actually run the whole data flow, taking from their source data all the way to the destination or the output data, and you should actually have that all executed. Once that's ready, it'll tell you when it's completed, and then your flow should be done, and you should see your data actually in the destination. So that is how the working with flows and data flow is very useful in Google Cloud. In this video, I'm going to describe the workflow that's associated with using data prep. So when it comes to data prep, we need to make sure that we understand what profiling data and how we actually profile our data with data prep. So just some basic profiling basics. When we use data prep, what we're doing is we're representing visual representations of our data for individual columns on an entire data set. And this is going to provide mechanisms for taking immediate actions on the issues of data that we see. So it's important that we profile our source data. So we're going to load our data into an application. You want to run a job to profile this data set before you even build a recipe at all. And these generated results are what's going to allow us to see what we actually want to do with the data. Because then we can actually start coming up with recipes. Once we have our data profiled, we can identify exactly what is inside of our data set and what we need to actually transform. So when you run a job in profiling, you want to choose a visual profile based on the job results from a run job page. And from those profiling in those job results, you'll be able to understand what kind of data you're dealing with. And this profile of our source data is useful for when we want to see how our data set has changed during our development process. So profiling in applications is quite simple. We've got things like the status bar. Now, the number of rows or columns and data types in the current sample are displayed at the bottom of a page in our status bar. You'll see things known as a column header. And this is the top of each column will contain what's called a data quality bar. And this is just so that we identify the valid, mismatched, and missing values in the columns. And then we have things like our column histogram. Now the bar chart at the top of each column in the transformer page is called a histogram. And then each column histogram is going to display the count of each detected value in the column. So specifically for string data, or if you want the count of values with the numeric range for number data. Now this histogram is really important because it allows me give me like a 1,000-foot view of what's inside of that column and what range of data is inside that column, especially if there's any null values or things that are missing. Now I can identify unusual values or outlier values, and then from there I can actually correct or remove this data. Another thing that is useful is known as column details. Now this is where I'll have things like statistics and outliers displayed in this detail window. I can view key statistical information on a column, and these displayed statistics are based on the column's data type. And so that's what you're going to start seeing. So you start seeing maybe an average or a mean or a mode, that kind of thing. And that'll tell you a little bit about the flow of data, the range of data that you're working with, if it's numeric, for example. Another interesting bit is the column browser. Now, this is where we can actually view our visual histograms for each column in the data set. And then I can make selections to identify correlations, even between the values in multiple columns, all in one go. And this is where the profiling in our applications come in so useful, because it's allowing us to very quickly do a basic exploratory data analysis on all of our data that we've collected. Now, when we have this kind of picture of what we're working with in our data, it's important that we move on to the next step, which is transforming our data. Now, transforming our data just means that we should start with visualizing our data. And this is important. Obviously, when we visualize our data, we want to display a sampled data. We could do this in a tabular format with visualizations to indicate particular areas of interest. For example, like a missing or invalid data or any type of outliers. We'll also have things like interactions. So I can even directly interact with the data to select things of interest in a graphical user interface, kind of like directly on the web console. So I can click a black bar in a column, for example, to select all of the missing values in that column if I choose to. Another useful bit is the prediction step. Now, based on the selections that I've made, the predictive transformation model will offer a set of suggested transformations that I could do. So I can select one from a list, such as a suggestion may have multiple variations for further refinement, such as removing missing data or null values. And I can even edit the suggested transformations directly and fine-tune them step by step for my use case if I choose to. Interestingly enough, they also have a presentation component to this. So each time I make a selection in the data grid or among the suggestion cards, you'll notice is that the effects of our selected transformations are then going to be previewed directly in the console in the data grid. And so I can immediately get that feedback very quickly to see if I'm making the correct transformations or not. And then what you want to do is then just cycle. You repeat the above steps for the next data of interest. So visualizing, interaction, prediction, and present, you just do this over and over again until you're happy with the actual data set that you've cleaned up and ready to go. And when it comes to working with our data set, there's different transformations that I want to discuss. So, we could deal with something known as sampling. And this is meaning if you have a very large data set, it can overload our browser. And that could impact performance. So what we want to do is we just want to work on a sample of our data, and we want to choose our sample data to be large enough so that it's statistically significant. When we analyze the sample, it's like analyzing the whole data set. And so that takes a little bit of mathematics to figure out what size of your sample, but what you're doing here is rather than working with the full data set, you're working with a small window of it. Another one is cleansing. Data cleansing task will address issues in our data quality, which is important when we're working with things like machine learning. And so this is where we're looking for things like consistency, reliability in our data set, and so forth. Changing our data types is important. Sometimes we need to cast them into a different data type for our use case. And then reviewing our histograms to actually get some type of, to be able to look at our data set, see the values found in the columns, and just get a visual representation of what kind of data quality we're working with in that column. And this is where the histogram will give me a visual representation rather than a numeric one. So it's a little easier for me to understand that. Assessing our data quality is important. And so I can actually create data quality rules to apply to the specifics of our data set. So if a data set includes square footage for rental properties, I can create a data quality rule that tests the square feet field values that are less than 0. Obviously, I can't have a negative square foot value. So I can put a data quality check there that automatically checks that column to see, do you identify anything that's less than 0? And then those values are going to be flagged in red in a data quality bar, and then I can actually select them very quickly in the console. Enriching our data is important for when we're working with data sets. We may want to take another data set and use it to sort of impute the data that's currently missing. So I can do some type of union or join operation. And then sampling, again, is important. So the data that you're going to use in data prep, if the data set is small enough, the sample is the entire data set. But for larger data sets, what's going to happen here is that there's going to be an initial data sample from the first rows of each data set, and you have to learn how to generate new samples. And this can provide different perspectives on our data, especially when we're working with complex flows. And profiles. So, when we're working with the transformation process, I want to be able to generate and review visual profiles of individual columns, and this is the way that I can do it. These profiles can be very helpful in identifying anomalies, outliers, really any issues that I have anywhere in my data set, and that's really important. When we're actually taking in raw data from an external source, is a very important feature. Now, sampling data using our data prep. So remember, a sample is just a selection of rows from our data. It's an initial data sample, and this can be used as the basis for building the transformation steps in our entire recipe. And this is going to automatically create initial data samples of our data whenever I create a new recipe for a data set, and it just enables me to create additional samples at any time. And so this is the idea of what an initial data is. When you create a new recipe and load it inside of our data prep transformer page, the initial data sample of the data set is going to be used. This data can consist of the first X number of rows of our data set, and X is going to be determined by a few different factors, such as the number of columns in a data set, the amount of data in each cell, the maximum permitted size of each sample. It's going to figure out intelligently how many rows of that data set is going to be attributed to a sample. Taking a sample, these first rows are display for us to begin in the transformer page, and this is where we can actually start creating our transformations. And so you might have to work with a few different transformer pages with your samples. You may have to run the transformations that you're working on multiple samples to make sure that they're working fine. So there may be significant changes in the data later in the time period while you're working on it. So you have to continuously take samples of our data, not with the full data set, but just a small portion of it to make sure that it's working fine. Now, when we have our sampled data, what we're doing here is we need to make sure that there's some sampling and memory that's in place. And so the idea here is when it comes to memory, is how much data is going to be stored in this memory, right? So when I perform a complex multi-data set operation, joins, unions, this recipe sample combination is going to consume a lot of memory. And so you have to be careful because you're basically running this in your memory. So as you, in your browser, right? So that's going to take memory from your tools. So as you add steps to your recipe without resampling, what's going to happen is your recipe and your sample are going to consume more memory in your browser. And this is where you're going to start seeing some performance bottlenecks. So it's important that you handle this. Performance in the browser can be impacted as memory consumption starts to increase. So you want to make sure that you have your selection of data or new recipe steps that can be slow to respond, and you could see the browser start to crash. So it's important that you manage this memory in your browser for this. There's also some key considerations that you want to talk about and some best practices that could be followed is the fact that you want to create a new recipe, add 3 steps to your recipe, generate a new random sample from that. And then, when you load that sample, it's displayed in our data grid. If you add 25 steps to your recipe, the 25 new steps are applied to the random sample in the browser's memory. And so that's really the best way to actually handle this, is to do consistent resample on what's inside of your browser's memory rather than just fetching new data each and every time. So those are just some key considerations when it comes to working with some samples in data prep.
In this video, I'm going to show you how we can actually create flows in a low-code environment called data prep and how we can actually configure everything. So I've got a few example data flows that I want to show and how to get it set up. So let's go ahead and get started by going to our Google Cloud Console, and up at the top, we're going to search for data prep. So we're just going to type data prep, and this is where you'll see that there's an icon that looks like this. It says data prep and data wrangling visual. Go ahead and click this, and you'll be met with a page that will take you to an external site that's created by Trifacta. And this is our first time setup for using Trifacta. There might be some agreements that you have to go through because it is a third-party software tool that integrates with the Google Cloud Console. So it just requires a location to save files. Go ahead and choose a bucket that you have, a Google storage bucket somewhere. I already have mine selected. I'm going to go ahead and click continue here and make sure that the project that you've selected is there. Mine is called valued bvoc, and this is the important thing here. So we're going to click continue, and the page here will take a moment to load. Now, here on the bottom, you can see that I've got some recently updated data flows. Up at the top right, there's 2 options called creating a flow or importing data, or I can just click create a new flow. I can even import data directly from cloud storage into BigQuery. Let me just walk you through some of these example flows that have been created for sales analytics use cases. Go ahead and click this one. You'll see that there's a few different flows that are done. I'll walk you through a bit of these to sort of see what's going on. So what we're doing is we are, what you're first seeing here is this kind of playground almost to actually create flows and see what's happening. So what you start over here on the bottom left, this is our source of data, which is from our cloud storage. There's something called salesopportunities.csv. So this is just our source of our data is just a flat file called the CSV. And this is where, as our first step, we recommend that you start by working by cleaning your data. So the first recipe that we're going to create is for cleaning recipes. So each of these icons that you see here is called a recipe. And each recipes are basically, if I click on one of them, you'll see that there's some steps that we use, right? So for the first step, we want to see what the data set looks like. For our transformation, you can actually open up the CSV file and see what's there. And then the first step is to start by removing any columns we don't need. In this case, it looks like I don't need this column, so I'm going to start removing it. And then there's, deleting this record type ID. So almost what you're seeing here are these slashes are comments. And the commands are going to be like a delete command. So here's delete record type ID column. And so we don't actually need that. So that's a column that's being deleted. And there are a lot of empty columns in the data set. So we'll delete 19 columns. So That's actually the recipe that we're following. And so there's a list of columns that we're going to be deleting. And then in here, you can see another comment where I can replace missing values in the is deleted columns with false, and replace matches of 0 with false as well. So this is kind of like our cleanup step, exactly what you might see. And there's 16 steps in here, including the comments. Each line has its own comment. I can take a look at the data itself, and I can click a preview and see, hey, this is what the data looks like beforehand, and I can start to see, okay, I need to delete some of these columns or actually do some data imputation. So that's kind of how these recipes kind of work. You're just using them to do some basic data transformations. And here we'll also do some second step where after we've cleaned our data, we'll do some calculations. And if I click on this, you'll see that I can actually calculating a new column called revenue from the amount by multiplying by 150. And creating columns from existing columns is a part of our data, like is part of our transformation steps. I would do this in Python or SQL, but in a very low code environment, anybody can actually do this very quickly. And this is kind of our flow chart. Now, from this output of this recipe, we can create a forecasted revenue per month. So that's another load of data. That could be one output. I could create a forecasted new revenue per source. That's another output. And I can even create this output here, which is sales per rep. And I can have the opportunity owner CSV come together with this data from our base calculations. And there will be a recipe here that'll show me how I can left join this opportunity owner CSV on the owner ID, which comes from our base calculation. And I can even pivot and create some data. So now I get to actually see some previews in here, and you'll see that, okay, this is the owner that owns it. This is their email. Here's the amount of money they have. This is their total revenue. And, I can see all of these things. The last time they've closed their sales and their min date and their max date for their close dates. So that is useful. And so now I've got these outputs. I can actually upload these outputs directly to the bucket, and that's the same bucket that's actually going to be reading from this data set. And that's pretty much it. That's how we can actually create these simple buttons here. And actually, then I can send this bucket CSV files that I've created and attach them to a data set in Google BigQuery, and I can create some visuals there in a dashboard, and it's as simple as that. So it's, if I click on the left-hand side here on flows, I can see a list of all of my flows here. One data set, 4 recipes for event log data. I've just showed you one for sales analytics use cases. If I want to create a flow, it's as simple as just going here to creating a blank flow, and this will be my template. So now I get to actually start with connecting my data, creating a recipe, and then sending that data as an output to the bucket that's attached to my data prep system. That's it. And that's how you can actually do this. Writing your code in here is very simple when you're recipes, and there's nothing, as you can tell, it's very slow code. So anybody can do this. You don't actually have to have an engineer, so it's abstracted a lot of the transformation steps that we need when we're working with any type of ETLs or ELTs. So that's a little bit on how we can use data prep in the Google Cloud Console.
In this video, we're going to describe the use case and components of the data flow service. Let's first understand what Google Data Flow actually is. So Google Data Flow is just a fully managed service that modifies and enhances our data in both batch or historical context and stream or real-time modes. Now, Google Cloud is just very good at data management and processing, and it actually will run Apache Beam pipelines for us. And this is a completely serverless, fast and cost-effective tools designed for batch and stream modes. Data flow has some key advantages that I want to discuss. Some of the benefits include things like fast analytics, and it has very quick speed as well for this. So data flow is enabled fast, simplified streaming. It's very easy to get set up with a data pipeline and development with lower data latency. And you'll have things like simplified management for all of our tools. So it allows our teams to focus on programming instead of managing these server clusters, since they're all serverless for us. Now, this serverless approach is what's going to remove a lot of our operational overhead from data engineering workloads. And you'll also notice that there's lower total costs of ownership, or TCO. And now this is going to be resource autoscaling paired with cost-optimized batch processing capabilities, and this allows us to use data flow so it's virtually limitless capacity to manage our seasonal and spiky workloads without overspending anything. And this is where this TCO is, with a very low TCO, is such an advantage with data flow. Here are some data flow use cases that we've used this before. So one of them is, yes, streaming data analytics. So we can actually organize and use some of the data from Internet of Things applications. So it'll be built alongside with PubSub and BigQuery. Our streaming solutions will built with Dataflow. Will provision the resources that I need to ingest, process, and analyze fluctuating volumes of real-time data for real-time business insights. And this is where we can actually use real-time artificial intelligence. So we can leverage things like Vertex AI and TensorFlow Extended, as well as Gemini within Vertex AI to enable predictive analytics, things like fraud detection, real-time personalization as the data is coming in. And there's many different advanced analytics use cases that can be done with Vertex AI and Dataflow going hand in hand. Another thing that's very useful is the sensor and log data processing. This allows us to unlock business insights from our global device networks using a simple IoT platform that's built right in. And this is a very useful thing because if we're analyzing real-time data, streaming data analytics from these Internet of Things devices, we have an entire platform here that allows us to understand those business insights from that data. And then we can use that data to actually leverage it with Vertex AI. And this gives us a very good ecosystem to work with data like this. Now, Dataflow features and components include things like Dataflow ML or Dataflow machine learning. This allows us to deploy and manage machine learning pipelines with ease. We can even use these machine learning models to do local and remote inference with batch and streaming pipelines if we choose to. We'll have Dataflow graphics processing units, or GPUs. This allows us to use optimized hardware for performance and cost of our GPU usage. And so there's a support for a wide range of NVIDIA GPUs within Google. And we'll have things like vertical autoscaling, so it'll dynamically adjust the compute capacity allocated to each worker based on the utilization. So if they're getting overbogged with work that they need to get done, then we'll actually vertically scale the system by adding more computational resources. And so this will work hand in hand with horizontal autoscaling as well to seamlessly scale workers to best fit the needs of the pipeline. So horizontal autoscaling will just allow the Dataflow service to automatically choose the appropriate number of worker instances so that we know what we need to actually run the job that we're working with. Now, this service may dynamically reallocate more workers or fewer workers during runtime to account for the characteristics of the job that we're running. So we'll always have the right size machines and the right number of machines to actually do the job that we're working with. Right fitting is going to create stage-specific pools of resources that are optimized for each stage to reduce resource wastage. And this is what's going to actually minimize our cost. And this is actually done underneath the hood by Dataflow. And it's quite useful. And it's part of the Smart Diagnostics, which is a suite of features that include things like job visualization capabilities that provides a user a visual way to inspect their job graph and identify bottlenecks within the job that they've submitted. And there's automatic recommendations to identify and tune the performance and availability problems that we're working with. Here are some Dataflow features and components that we can work with. We have things such as a streaming engine. Now, this will use the separate compute from state storage and moves parts of the pipeline execution out of the worker virtual machines and into a Dataflow service backend. So that's very useful. It's going to significantly improve our autoscaling and our data latency, and this is the job of the streaming engine. We'll have also a Dataflow shuffle as well. So this is very useful. It's a service-based Dataflow shuffle that moves the shuffle operation. It's used for grouping and joining our data when we're working with worker virtual machines and into the Dataflow service backend for batch pipelines. Now, these pipelines will scale very easily without any tuning required on our end, and it'll actually work with hundreds of terabytes on that scale of data. So if you're working with hundreds of terabytes, This is what's going to help us with that. We also have a language Dataflow SQL that lets us use our SQL skills to just develop some streaming pipelines for us. And it's actually able to work directly from the BigQuery web user interface. So that's where we'll write our Dataflow SQL. And this is where I can join streaming data from PubSub, for example, with files in cloud storage or tables in BigQuery. And I can even write the results into a BigQuery table, and I can even build a real-time dashboard from that table to allow me to see how things are working with. So it'll actually slot right into the BI tools that I'm working with, which is quite useful. Another thing that we'll have is the flexible resource scheduling, or FlexRS. This is what's going to reduce our batch processing costs, and it's going to do this by using what's known as an advanced scheduling technique, such as the Dataflow Shuffle service, and a combination of virtual machine instances and regular virtual machines. And what you'll notice here with the Dataflow templates, this allows us to easily share our pipelines with team members across our entire organizations, and this will allow us to take advantage of the Google provided templates to implement our own development. So there's no need to actually reinvent the wheel. There's ones that are available for us to use from the scratch, and we just have to modify. And so we'll have things like change data capture templates for streaming analytics use cases, for example. And you'll have things like flex templates where I can actually create a template out of any Dataflow pipeline if I choose to, and then share those accordingly with my team to help reduce development cost. Here are a few more features that I'd like to discuss. We have notebooks integration. So I can actually build pipelines from the ground up using a Vertex AI notebooks, and I can even deploy those pipelines with Dataflow Runner. I'll have things like real-time data capture, which allows me to synchronize or replicate my data reliably with minimal latency across different data sources. And this allows me to power my streaming analytics a little easier. And I can actually replicate data from cloud storage into BigQuery, into PostgreSQL or Spanner. It's up to me on what I want to do. And so using this real-time change data capture is quite useful for that. We'll also have things like inline monitoring. So this allows us to directly access things like job metrics to help with troubleshooting batch and streaming pipelines. And we'll also have a customer managed encryption key, so I can create a batch or streaming pipeline that is protected with my own encryption key, or I can use the ones that are provided by Google as well. And we'll have Dataflow VPC service controls. So this is where the integration with our VPC service controls will provide additional security for data processing environments, and just make sure that we are able to mitigate the risks of any data exfiltration. Private IP addresses is also available, so I can turn off public IPs, and this allows me to better secure my data processing infrastructure. This means that the IP address is not going to be accessible from the outside, from the internet. The only thing that will be able to access this system will be anything within the VPC, my virtual private cloud, inside of my Google project. And so this will allow me to lower the number of public IP addresses I consume against my Google Cloud project quota, and also just allow me to keep things very safe and secure so that no one can access the infrastructure. And that is some of the features that come with Dataflow and some of the use cases that we can use it for.
In this video, I'm going to talk about how we can create a Dataflow pipeline script, and also talk to you a little bit about the contents of this code. Now, this code is, it can be kind of terse. So what I'm going to do is I'm going to provide it in the video as a file. And so this is the thing that I wanted to kind of walk everyone through. So as an attachment, you'll have the file here, and I'll walk you through what's happening with each of these things. So creating a pipeline script involves using what's called the Apache Beam SDK, and this is supported using Google Cloud Dataflow. Now, Apache Beam is just a unified programming model that enables us to develop batch and streaming data processing pipelines. That's it. So the first step that we want to do is open up our terminal in VS Code and install the Apache Beam package for Python. So I'm going to use pip install space Apache -beam, and I'm going to hit enter. And what this will do is, now I've already have it installed, but this will take a couple of minutes for you to install the Python package. So all of this is being done in Python. You can do this in JavaScript or another programming language, but primarily I would recommend that you do this in Python for this kind of thing. Any data work like this, it's really the best tool for what we're working on here. So now
What I'm going to talk to you is kind of going through each step here. There's a few different pieces to this script and it's kind of long. So what I'll first start is talk about the imports at the very top. So I'm importing Apache Beam. So this is the core Apache Beam model. That's our very first thing that we do. And then from there, I can actually start importing different pipeline options that are used to configure the pipeline. And so there's Google Cloud options that'll contain what's options for our Google Cloud platform project specific options, such as your project ID and your region, things that you're actually going to be connecting with in the cloud. And then there's the standard options. These are going to include options like our runner type, including things like our data flow runner. And then there's another thing that I like to use from Apache Beam for input output, and this is just allowing Beam to write data into BigQuery. And then there's argparse, which is just used for parsing command line arguments. When I actually run this, I can provide some arguments this way. Okay, so what'll happen here is the next thing is we're going to talk about is defining our pipeline options. So this is where you'll see I have a class that's defined, which is pipeline options, and I provide, it's going to be inheriting from a class that I've already imported called pipeline options. So this is where I can actually have a class method in here that says add argparse.arg. So this is a custom pipeline option class to handle specific input and output parameters, which is what you're seeing here. And then there's the _add _argparse _args. This is just a method that's used to define custom arguments. And I can have an input for the input file path or output for the BigQuery table, that kind of thing. And it tells me what type that I want to use. So that's really all this is for. Okay, so that's what we're using this for. So now let's go ahead and talk about the run function. This is pretty important. So the run function takes 0 arguments by default, none, but you can actually pass in some arguments to this. So the first thing we're going to do is talk about pipeline options. So this allows us to parse the command line arguments and set up the pipeline configuration. And it'll also have Google Cloud options and standard options. So these are, again, this is just allowing, as you can tell here from my Google Cloud options, I am setting my project ID, my region, my job name, pretty much anything you're seeing here, especially with a staging location and a temporary location. And it gives me some more pipeline options that I can use, such as data flow runner. So this allows me to set the runner for the flow itself. So these options are, as you can tell, is just settings for my Google Cloud account. And if I scroll down here, you'll see that there's a defining the pipeline. So with beam.pipeline, so it's options equal to pipeline _options as P. So this is just a context manager. I'm now defining my actual pipeline. So this is where I'll start off with beam.pipeline. This allows me to create the pipeline object with specified options. There's also a read from text as well that's there. And there's a map as well as write to BigQuery. Now, this read from text just reads data from a text file in Google Cloud Storage. I'm assuming that the file is going to be in CSV. Depending on my use case, it could be a different format, such as XML, anything really. I could open it up. But for now, let's just assume that it's CSV. That's how I've written my code. I can apply transformations to each element on the collection of pipelines here that I have, PC collection. And I can also write to BigQuery. And that is essentially what's going to happen is I'm writing process data to BigQuery, and I'm following this kind of operation here. And I'm giving it some options there to actually write to BigQuery. And then finally, once this is all done, I can have if name is equal to main, and I can run this code. Now to run this, I can actually just run this pipeline on Google Cloud Dataflow. I can upload this directly to a Google Cloud bucket and give it a input file and an output file, like in other words, a data set and a table that I want this to write to BigQuery. And then that's it. Then I can actually run this system and take some CSV files and then output that to a data set. And that's pretty much all we have to do to create a very simple deployment script for this data flow. And that's really all we have to do. So that's our pipeline script. In this video, I'm going to discuss how we can create a data flow pipeline deployment script, and I'll talk a little bit about the contents of this script. So deploying a data flow pipeline involves creating a script that sets up and runs our pipeline on Google Cloud Dataflow. The script is usually written in Python, and we're using a Python package called Apache Beam, and it includes configurations for the data flow job and input and output data locations, and Google Cloud project settings and runtime options. So let's go through this step by step. So it's a pretty big script. So what you'll notice here, the very first thing that we're doing is we're importing our Apache Beam on line 1 as Beam. These are just core Apache Beam modules that's used to define and run the pipeline. We'll also see that we're importing things such as pipeline options, and these are just general pipeline configurations that are used for the settings for the pipeline, including things like Google Cloud options that contain settings for our Google Cloud system. Now, the Google Cloud options are just specific configurations that we'll use, such as project ID and region that is typically associated with using cloud environments. And there's also standard options, such as specifying the runner. In this case, we're going to be using data flow. And there's setup options, which includes the options like having the main session to handle global variables and imports. And we've got my pipeline options classes here. And this is where we're going to be creating a class that is extending the pipeline options class that we've imported. And it's to handle additional input and output arguments. So that's really important there. So this is where we're going to have input and output systems in place. So parser.addValueProviderArgument, those kind of things are what's used. Now, the add argparse or args will define command line arguments for the input file and our output table. This is just a way for us to actually pass in exactly what is our input file. In this case, I'm assuming our input file is going to be a CSV, and our output is going to be to a BigQuery table inside of a data set that we have created. So I'll come back to how that looks a little bit later when we actually start to run this information. So if we wanted to provide an input, it would be Python space pipeline deployment example.py. That's the name of my file, space, and then I will give -- input and then space, and then give it a string, which would be a path of the input file to read from. In this case, it would be like a Google Cloud storage bucket, and it's as simple as that. So it's basically we're defining what our command line arguments are for. The pipeline configuration is where we're actually going to be defining it here in the run step. So I've created a pipeline options object, and I've created a gcloud options object as well. So I can start to give some gcloud options, such as my project ID, my region that I'll be working in, what my job name is going to be called, what my staging and temporary locations are going to be. As you can see here, they're Google Cloud storage buckets, so I can actually use them there. I also have a setting here to set the runner option. In this case, I'm going to be using data flow. So this is where I can get the standard options, the runner, and set it to be the data flow runner. And that's pretty much it. That's what we can do there. Now we can set up additional options, and that's where we can actually have the setup options, which will allow me to save the main session. So this is where I can ensure that the main session state is saved, including things like global variables and imports, so it's available to all worker nodes. These are just some settings to actually work with the actual pipeline. Now I get to actually define the pipeline, and I can define the pipeline with beam.pipeline_asp. Now this is just a block of code that's going to define the pipeline. It's going to ensure that all operations within the block are executed as part of our pipeline. And so the first thing I'm doing is I'm reading from text. This will read data from a text file stored in Google Cloud Storage. It could be a CSV file, it could be an XML file. The point is it's some type of flat file. Then I have the map, which will transform each line of the input file by splitting it into fields. In this case, it would be columns. And then finally, I have the write to BigQuery command. This will write the process data to a BigQuery table, and the schema is then going to be specified, and write truncate ensures that the table is replaced if it already exists. And I can use create if needed, ensures that the table is created if it doesn't exist. Finally, at the very last step, you'll see that if the name is equal to main, this is run. So I'm going to be calling this as our entry point, and this will actually run all of our code that we need to run. And then I can just go ahead and run this script in the terminal. And that's pretty much all we really need to do to get this to take a CSV file from a Google Cloud storage bucket and deploy it on the Google Cloud data flow to run some data transformation
and send it over to a BigQuery dataset. In this video, I'm going to identify the use cases for selecting various options available when running a data flow pipeline. Let's first understand some of these options in detail. Data flow options consists of basic options, and what will happen is you'll have things like a system of data. So, for example, if I'm working with Java or Python or Go, there will be different types of options that I can have. So there's data flow service options, which will specify additional job modes and configurations. And they'll also provide backwards compatibility for different SDK versions that don't have explicit pipeline options or later data flow features. So if I'm working with things like simple Apache Beam SDK, for example, there are multiple service options that are available for that. And so depending on the tool that I'm working with to transform my data, these basic options can come forward. And so then you'll also have things like your resource utilization, which we'll talk about the auto-scaling mode for our data flow job. So I can have values such as throughput based, for example, to enable auto-scaling, or I can have it none to completely disable auto-scaling. There's different auto-tuning features that could be available, and depending on what streaming engine you're using, you can actually have different behaviors. Now, it's too much to go into all of these settings for basic options, but just know that for basic options and resource utilizations, there are many different options that are available. So, for example, if I want to use things like Flex Resource Scheduling, FlexRS, those are for auto-scaled batch jobs that could affect the number of workers, auto-scaling, zone, region, all of those things will be done for us. Now, those settings are going to be done primarily by the Google Cloud console underneath the hood, but just know that they exist there. So when you're actually looking to set up these options, that's what's there. Another really important one is the debugging. So whether you're working with an SDK from Java, Python, or Go, you'll have things like hotkey logging enabled, which is just a Boolean that is either true or false, and it'll specify when a hotkey is detected in the pipeline. So it could be a literal, a human readable key is printed in the user's cloud logging project. It'll notify you and let you know. These are just some of the debugging options that are there. This is the one that I find the most useful, so that when I see that there's an error, I get an alert to let me know that my data flow pipeline has failed. Now, some more options that include things such as security and networking. So I can specify, for example, a data flow KMS key. It specifies the usage and the name of what's known as a customer managed encryption key, or CMEK. And this is used to encrypt data at rest. I can control this encryption through the cloud KMS, or I can also specify my own encryption key. And if it's unspecified, Dataflow will use the simple Google Cloud encryption instead of my own, and that's perfectly fine. But you have to give it either your own or you have to use Google's. You can't leave it unencrypted. We'll have a streaming pipeline management as well. That's quite useful. And so this is where we'll have some settings that deal with the streaming pipeline. So it'll specify the snapshot ID, for example, to use when creating a streaming job. Snapshots will save the state of a streaming pipeline and allow us to start a new version of our job from that state if we choose to. And we can a few more different ones that I can have is some worker level options. One of them is called the disk size gigabytes. It's an integer that you provide. This is essentially what it sounds like. It's a disk size in gigabytes to use on each remote compute engine worker instance that it's attached to the data flow pipeline. If you set it, you specify at least 30 gigabytes to account for the worker boot image and the local logs that could be generated, and that's what's going to be done there. Another thing that we have is some other local pipeline options, and these are just some miscellaneous options that don't fall within the others. And these things are useful, so I can find some default values for pipeline options in the Apache Beam SDK for Java references on the Google Cloud console. So when my pipeline is using Google Cloud products such as BigQuery or Cloud Storage for input-output, I might need to set certain Google Cloud projects and credential options. This is where I would do it. And so there's a setting that can be set there. And this is where it's going to allow me to set my Google Cloud project ID. And I may also need to set credentials explicitly. This is where those other local pipeline options will work. And there's different ones that are available to see. There's many different options in each of these categories, and there's just too much to go into detail in this video, but just know that they exist. And you'd have to look through the Google Cloud data flow
documentation to see exactly how these things will work. Another one here is for options for setting the pipeline streaming mode. So this is what you might think. If you're setting this pipeline streaming mode, Dataflow supports 2 modes for streaming. Exactly once mode. This means that the mode is the default for all Dataflow streaming jobs. What this does is that Dataflow is going to ensure that records are not dropped or duplicated as the data moves through the pipeline. We'll have an at least once mode, and this is different because this is a mode that guarantees that records are processed at least once, and there are duplicate records that are possible in this mode. So for use cases that can tolerate duplicates, I recommend that we use the at least once mode, and it can significantly lower the cost and latency of our job. But if you can't have duplicates, then the exactly once mode is the one to use. And so starting a streaming mode is important. So once you've identified which streaming mode you'd like, you can set that streaming mode directly in the Google Cloud Console. And then you can go ahead and select a streaming mode from a template if you choose to, and rather than making one yourself. And this just allows me to use, I can run Dataflow streaming template to perform a few steps that I otherwise would need to create. And this just involves using one that's already created in the Google Cloud Console and then maybe modifying it for my use case. I can even view a job's streaming mode, and I just have to go into the jobs page in Dataflow, and the streaming mode is listed on the job details page in the job info panel. And that's where I can see exactly what streaming mode I have selected for that job, and if I'm using a template for this job mode, for the streaming mode. A few more options here that I want to discuss is that, when working with data sets, specifically with images or videos, I recommend using GPUs with Dataflow. This brings the accelerated benefits directly to our stream or batch data processing pipeline. So I can simplify the process of getting data to the GPU with Dataflow. And it's very good for those kind of high resolution images and video. That's what these GPUs are very good at. And so this gets me all the benefits, the fully managed Dataflow system. So I can use things like host provisioning, auto-scaling, fault tolerance, and more. And I'll have things like Azure Resource Manager or ARM VMs on Dataflow. And what this means is that I can use the Tau machine series of ARM processors to run Dataflow jobs. And this ARM architecture is optimized for power efficiency. And using these VMs will yield to better price per performance rather than using the x86 types of processors from Intel, for example. And so ARM processors are great for this kind of processing. And so there's different hardware requirements or software requirements when it comes to using ARM processors. So for example, Apache Beam SDK support ARM virtual machines. You just have to make sure that you're using a certain Java SDK version that's greater than 2.50.0. And then that is what's really going to give you the best performance on those machines. So that's a little bit on how we can use Dataflow and some of the Dataflow options that we can set, as well as just some tricks with hardware that we can use to actually optimize our performance.
In this video, we're going to describe the use case and components of the Data Fusion service. So let's take a look at Google Cloud Data Fusion. Data Fusion is just a fully managed, cloud-native enterprise data integration service, and it's just meant for building and managing our data pipelines. It's very low code and has a point-and-click interface. This visual point-and-click interface enables our code-free deployment of any ETLs or ELT data pipelines that we're trying to deploy. It also has some pre-configured connectors and transformations so that we can use them at no additional cost to connect to different sources and destinations. So I can go ahead and use them to connect to a Postgres database or connect to a BigQuery table, and then I can use some out-of-the-box solutions for some transformations that are available. It's very good at end-to-end data lineage. So I can look at for root cause and impact analysis on certain pieces of data or certain trends that I see in my final data set. It has pipeline portability. So I can actually use these across multiple different pipelines that I choose, and I can use them across different projects. And this is where I get my open source core, or CDAP, for pipeline portability, and I can use this across many different tools for this. Now, Data Fusion use cases are great. So there's a few different ones that I want to talk about. Is that they're great for modern, secure data lakes on Google Cloud, and helps us build scalable, distributed data lakes with Google Cloud and by integrating data from siloed on-premises platforms. And I can leverage the scale of the cloud to centralize data and drive more value out of data as a result. I also have things like agile data warehousing, so it can help organizations better understand their customers by breaking down data into silos and enabling development of agile cloud-based data warehouse solutions in BigQuery. Now, one thing I've noticed is that it has the best unified analytics environment. It's actually great for this. Many users want to establish a unified analytics environment across a myriad of expensive on-premises data marts. Well, I can employ a wide range of disconnected tools that's just really hard for me to work with. Cloud Data Fusion will give me a vast variety of connectors and visual interfaces, an abstraction centered around business logic that helps me get the best analytics environment so that I can actually visualize my data, and I can look at self-service and standardization, as well as reducing repetitive work across those different data marts by unifying them into one cohesive dashboard. Now, here are some features that are involved with Data Fusion. So we've got things like codeless self-service. It removes any bottlenecks by enabling non-technical users, using a code-free graphical interface that delivers point-and-click data integration, very simple for us to use. It's abstracted that kind of engineering away from them. And we've got collaborative data engineering, so it offers the ability to create an internal library of custom connections and transformations that can be validated, shared, and reused across any organization. And we've got Google Cloud Native. So this is a fully managed cloud native architecture that unlocks the scalability, reliability, security, and privacy features of any Google Cloud service, but it's all native to the Google Cloud, so we get to leverage the security that's offered by Google Cloud. Some more features that are great, which is the real-time data integration. So I can replicate transactional operational databases such as SQL Server or MySQL, and I can even replicate them directly into BigQuery simply with just a few clicks using Data Fusion's replication feature. It's actually meant to use from our transactional database into a data warehouse such as BigQuery. Just a few use cases there that are available, and we have integration with DataStream that allows us to deliver change streams into BigQuery for continuous analytics, not just a simple batch dump of data. Batch integration allows me to design, run, and operate high volumes of data pipelines. So it's periodically going to support for popular data sources, including file systems and object stores, but also relational and non-relational databases, including things like software as a service systems and mainframes that are available. So it's actually very useful for different products that you're using, and it has enterprise-grade security. In fact, I'm using integration with cloud identity and access management. Things like private IP addresses and customer managed encryption keys will provide enterprise security and alleviate risks and ensures the compliance and data protection for all of our data pipelines that we're using. Some more features I want to discuss here is the integration metadata and lineage, which is quite useful for this. So it's search integrated data sets by technical and business metadata. I can track lineage for all integrated data sets at the dataset and field level. I have things like seamless operations. So this is REST APIs, time-based schedules, pipeline state-based triggers, things like logs and metrics and monitoring dashboards, and they make it easy to operate in mission-critical environments as well. I have an integration toolkit that's built in. So a variety of legacy systems can be supported, code-free transformations. I'll even have things like conditionals and pre-post processing. My tool that I use the most is alerting and notifications. So it allows me to see that what's happening when a certain error happens, and error processing provides a comprehensive data integration experience in one location. Hybrid enablement is another key feature with Data Fusion. This means that open source tools will provide the flexibility and portability required to build standardized data integration solutions across hybrid and multi-cloud environments. So whether I'm using Google Cloud and Azure or AWS, or using Google Cloud with my on-premises environment, hybrid enablement is supported with Data Fusion. Another thing that I want to discuss here is known as the component of Data Fusion, which includes things like a tenant project. So these are just services that are required to build and orchestrate cloud data fusion pipelines, and we just want to be able to store these pipelines and its metadata so that they're provisioned in what's known as a tenant project.
This is known as a tenancy unit. You'll see it. And a separate tenant project is created for each customer project that we're working with. So Cloud Data Fusion instances are provisioned, and the tenant project is going to inherit all the networking and all the firewall configurations from the customer project. So it's just a way for us to containerize our Data Fusion. As well, we have the Cloud Data Fusion console, which is a major component of Data Fusion. This is referred to as our control plane, and this is just a set of API operations through a web interface that deal with the Cloud Data Fusion instance itself. So I can do things like create, delete, restart, and update my instance. And I'll have Data Fusion Studio. This is referred to as the data plane, not the control plane, but the data plane. And again, this is just a set of REST API and web interface operations that deal with the creation, execution, and management of our pipelines and any of its related artifacts, such as flat files that are generated or what have you, any other files that are going to be generated from the pipeline. That's what's going to be done here in the Data Fusion Studio. Okay, so that is a little bit of the components of Data Fusion, as well as some of the Data Fusion key features and use cases that are offered.
In this video, I'm going to identify the options associated with Data Fusion instance and pipeline creation. Let's first get started with understanding the instance creation in Data Fusion process. After we create a Cloud Data Fusion instance, we can't change any of its additions, so just keep this in mind. So after creation, instance versions cannot be changed. And how we do this is it's all done through the console. So I go to the Cloud Data Fusion page, I click my instances, and I click create an instance. I enter some information, such as the instance name, description, and the region in which the instance is going to be operating in. And I can specify things like the version and an addition. And the default here is just set to basic. So after these creation options for cloud logging and monitoring and private IP cannot be added or removed. So you have to have these things already in place upon instance creation. So that is a little bit on what happens. It takes about 30 minutes for the instance creation process to complete. So it's actually spinning up all this information. And so then what we can do is then, if this is the general way to create an instance, we can actually break this down into a public instance, for example. If I want to create a public instance, I need to enable the Cloud Data Fusion API. That's key here. And this is where the permissions for actually using the instances create is going to be there, as well with different access control. We'll have configure instances or create permissions as well. And so this is for information about the types that we can use in terms of what instances and what permissions are going to need can all be found underneath our service accounts. And what I'll notice here is that I can ensure a project meets Dataproc requirements. So default Cloud Data Fusion executes our pipelines using what's known as a Dataproc cluster in our project. Make sure that your project meets this Dataproc networking requirements. And these networking requirements there's a list of them, and you can find them on the Google Cloud Console. It's hard right now to go through all of them in this video. It's outside the scope, but just know that they exist. And we want to be able to configure a firewall and some type of default network. So the default network is pre-populated with a firewall rules, for example, to allow SSH. And that allows incoming connections on a TCP port 22 for SSH from any source to any instance in the network. You want to make sure that you allow ingress on TCP port 22 and it doesn't exist in the network used by your Cloud Data Fusion instance. So you have to make sure that you create that rule for this to work properly. Now, once you have this, you can create a private instance with a VPC pairing, for example. So this is where I need to first set up a VPC network or a shared VPC network. And a private Cloud Data Fusion instance has the following benefits. For what you're going to notice is that connections to the instance are established over what's called a private VPC network in our Google Cloud project. So traffic over the network doesn't go through the public internet, which is useful for that. The instance can connect to your on-premises sources as well as relational databases, because the on-premises network will connect to the Google Cloud private VPC network through a VPN or Cloud Interconnect, and I can access my on-premises resources as well. So setting up our VPC network peering is really important. So that is the network to be able to connect between, like I said, the cloud and the on-premises, for example, who's going to be connecting to the system. So your instance needs created in its own VPC, and you might need to set up a VPC network peering to connect with the source and the sink that you use in our pipeline. So this is what's important after we've set up our VPC. Finally, there might be some connection use cases you want to know is that when you're working with these connections, you may want to enable, private Google access. So Data Fusion must create the data prod clusters and run the data pipelines in a subnet that has private Google access. So that's quite useful. You have to make sure that you enable private Google access for the subnet that contains the data prod cluster. So that's important. And then you might be able to connect to other sources if you'd like to. It's optional, you don't have to. So after you create a private instance in Google Cloud Data Fusion, you can connect to other sources. So an on-premises database, like I was mentioning earlier, I can connect to Google Cloud services running in their own network and private node, such as Cloud SQL, or I can even connect to different sources on the public internet. It really starts to open things up a little bit. And so that is a little bit on the private instances with VPC peering. Now I can create a private instance with what's called Private Service Connect. So this is where I can configure Private Service Connect, which is the first thing. And this is subject to the using a Private Service Connect is going to give us a Private Service Connect interface that provides the way for Cloud Data Fusion to initiate private and secure connections to other consumer VPC networks. It allows us to configure our security a little more granularly as well by providing what's known as a shared VPC if we choose to use that. So that's the idea of creating a private instance with a Private Service Connect. Configuring this Private Service Connect is all done through the console, or you can use the command line interface to do all this. I recommend doing it with the console. It's a little cleaner to do it that way. And there's where I can start to configure my security, and my deployments of Private Service Connect's interface can be done through there. And that is one thing I'll say about the creating a private instance with Private Service Connect. And so creating a data pipeline comes down to first understanding to create a Cloud Data Fusion instance, which is important. You also have to deploy a pipeline. And from there, once that pipeline is deployed, you still have to execute that pipeline. Now, either that can be done by a trigger from a pub sub, or you have to do this manually yourself. And then once that pipeline has been executed, we'll have to move on to reviewing the results. And this can all be done directly in the Google Cloud console itself for data pipelines. You can see everything that's there. And then finally, you get to clean up any of the leftover pipelines that you don't actually need to use over and over again. So this is where I recommend that you avoid incurring charges for the resources used, and just delete the BigQuery dataset or any other system that you don't actually need, any intermediary source, because that's really important because you are going to be charged for the system being up. And if it's idle, you may want to actually turn this thing off before you incur any further charges on your projects. And so that's just a little bit of the step-by-step flow that I work with when working with Cloud Data Fusion instances and pipelines. This is what this system is, and that's all. In this video, we're going to describe some of the options that are available for configuring instances, pipelines, and connections in Data Fusion. Let's first understand the backing up and restoring instance data process and how this actually works. So what happens here is when we have any type of instance, we want to be able to have some backup in place so that in case of disaster, we get to recover that instance back to its original state. Now, I can back up and restore a few different types of information, and it's all done through the Cloud Data Fusion REST API. And it's important for us to fully restore data pipelines. We must recover all of the dependent information, and there's different dependencies that we have to worry about. So to restore, we want to import from our Cloud Data Fusion UI, which is all done through the Google Cloud Console. And then that's what's actually going to allow us to do any type of retrieval. And so this lets us adjust the version number in the pipeline JSON. It allows us to do a deployment directly through the API, and it requires a proper JSON adoption all the way through. So that's how we do these. We're basically at the core, we're using these REST APIs and using the UI to make those REST API calls for us. And that's what's going to allow us to restore everything. So that's one setting that we should be worried about. The next thing is we need to be able to edit our pipelines. So this means that there should be some editing capabilities and our options that are available. So when we edit a pipeline, we need to do a few things. We need to incrementally add features to a deployed pipeline without creating duplicates. So that's one of them. So I can add, remove, or modify plugins, and then I can redeploy the pipeline itself. So I'm still having one pipeline without any duplicates. So editing a pipeline will create a new version of the same pipeline, which could prevent proliferation of pipelines. And this just allows for better organization. If you duplicate a pipeline, it'll create a new pipeline with a different name. So that's something to be wary about. And viewing or restoring previous versions becomes easy because now I have a history of all the edited versions of my pipeline. So, if I make a setting and it's not performing the way I want it to, problem, I'll just go back to the previous version. So there's like a little bit of a version control system built into these things. Not only can I edit the pipelines, but I can also export the pipelines. So exporting an edited version of a deployed pipeline means that we're going to export the most recent version of our pipeline, and it's going to be deployed not as a JSON file to share with other developers. Somebody else can take that JSON file, they can add it to version control, they can move it from a development environment to a test or production environment. So after I edit a pipeline during development and the debugging phases, I can export that JSON file and then import and deploy it in a production-ready environment, all done directly through the Google Cloud Console. And it's allowing me also to export a previous version as well, not just the latest version. So this is all done directly in the Data Fusion interface. On importing edited versions of deployed pipelines, so now that I have a pipeline, if somebody's made an edit to it, they give me the JSON file. Well, how do we do this? Well, I can delete edited versions if I need to, but I can also edit the pipeline statuses as well. So when you delete the latest version of a deployed pipeline, all versions of the deployed pipeline are then deleted. And so draft versions aren't deleted. What you want to do instead is draft the pipeline version that has an orphan status, and then I can resolve those statuses to deploy that draft pipe. Now, Cloud Data Fusion creates a brand new pipeline, which is just going to be the latest version. And so different statuses such as orphaned or obsolete. So for example, orphaned, this just means that the latest version of the pipeline was deleted and associated drafts are no longer belong to an existing pipeline. That's one of them. Obsolete means a newer version has been deployed while edits have been in progress. So you might see the status of another developer deploy the pipeline before you finish editing the current file that you have. And so this is really useful. It's the same if you see it called draft out of date. That's the same thing. It just means that kind of thing. Now, if you see a description of in progress, it just means that you have saved edits to the pipeline that you still need to deploy. Here's how we can also manage some connections as well. So managing connections means that we get to create a couple of things. So we first have to create the connections. So this involves creation. And so creating a connection in the Cloud Data Fusion web interface is important. You can do this all in the Cloud Console and just use that to add connections. I can click the type of connection that I want to create, such as BigQuery. That's one of them, and it's all there in the system. I can also use connections in a plugin, which is useful. So when I use connections in a plugin, what's happening is the plugin is going to inherit the connection properties that you configured in the previous step when you actually created the connection itself. And so that's quite useful. And what you can do is that there's different source plugins that you can use. So there's different batch source plugins such as Amazon S3, Query, Spanner, Cloud Storage. All of them here are available for them to use inside the console. And so you can also then just add connections if you choose to. So there's browsing connections and adding connections are two of the operations that you can do. Adding connections just means you want to make sure that you have your actual source system ready to go. And that could be anything, right? It could be a BigQuery table or an S3 bucket, anything at all. And then there's an add connection page that allows us to select the type of connections that we want to create. And that's just dependent on what the source system is. Once those connections are created, we can even edit the connection properties directly in the console. And we can also create any duplication or duplicate connections so that we can use them somewhere else and just have a version of it that can be used by something else if we need to. And that's really what we can do here. Those are the ideas of managing connections. A couple things here on managing connections. Remember, we can also import a connection from another JSON file. So this means that we can take a JSON file that's coming from another Cloud Data Fusion project or pipeline and use it in our current one. We can also export a connection so others can use it just like that. And finally, we can also delete the connection directly in the connections page on Data Fusion. And that is the concepts of managing our connections and what connections are inside of our Google Cloud Console. In this video, I'm going to show you how we can actually create a pipeline in Data Fusion using the built-in Google Cloud Data Fusion Studio tools. And so it's going to involve several steps. So Data Fusion, again, is just a fully managed cloud-native data integration service and allows us to design and manage our data pipelines using a graphical user interface. There's a step-by-step guide I'm going to follow with you here, just so we can do this one step at a time. So the first thing we're going to do is we are going to search for Data Fusion Studio, Data space Fusion up at the top here. And so you'll see that there's Data Fusion, which is Data Pipeline Management. We're going to go ahead and click that, and we're going to be met with this page. It's going to allow us here to go ahead and click Enable for our API. Totally normal if you haven't actually enabled the API before. This is what we're going to be doing. It takes just a moment for that to happen. After the API is enabled and billing is enabled for this service, we can go ahead and start creating a new pipeline. And so what we're going to do is we are going to just get to this first step here, which is going to be creating an instance. That's our very first thing that we're going to do. So we'll go ahead and click Create an Instance. I'm going to give it a name. I'm going to give it Create an Instance. I'm going to give it my-example-instance and give it a region here. I'll select US Central 1 and I'll scroll down. I'll just use Basic Edition here for now. And we will not add any accelerators. We'll grant some permissions that's necessary. So that's fine. Let's go ahead and click Grant Permission. And we are going to then scroll down here. And that's pretty much all we need to set up. Is just choose the edition, the region, and everything else is going to be done for us. Again, this is a fully managed service. So I can go ahead and click Create. This will take approximately 20 minutes to actually get this spun up. So I'll pause the video and just wait and come back when it's all ready to go. Okay, so now that our example instance has been created, the next step that we're going to do is we are going to then click the instance itself, go into it, and we can start creating our pipeline in the studio. So on our left-hand side, you can see here's our instances. If we scroll down, you can see all the settings here are ready to go. We can click View Instance URL, and it'll ask us to sign in. Let's just make sure that we're ready to go. Might have to do some acceptance criteria here for this. You're here now in the Cloud Data Fusion, kind of the example instance itself. This is how we can start doing some type of integration or system or wrangling our data. We're going to go ahead and click on the left-hand side here, the 3 dots, and then this little namespace will pop up. We're going to be in the default namespace, and we're going to be here in the pipeline. We're going to go ahead and click Studio. Now we're in the Data Vision Studio here, and what we're going to do now is this is where we can actually start creating our pipelines. So we can add a source in our data. So here, as you can tell, these are all the different sources. So if I wanted to be, for example, a BigQuery table as my source, I can just click and drag or click this, and then it will put the BigQuery properties right over here. And now this will be my source of my data. I can actually click the properties itself. I can add a comment, I can delete it, I can click properties here, and these will be the settings for the the input path of what I want to do. So I can actually have a project ID as auto detect. I can detect what my project ID is. I can browse the data set that I'm looking for. I can give it a table that I'm looking for. I can ask it to get a schema. Basically, these are all the settings on this input source that I have. Now that I have the source, I can go ahead and click a transformation layer. So maybe there's for example, I want to do some type of compressing or some parsing of CSV files or formatting some CSV files, or maybe I want to have some custom JavaScript code to actually read the data from the BigQuery table that I've selected. Or maybe I can have some type of wrangler. Let's say if I have a JavaScript code here, I can pass this BigQuery table directly to the JavaScript code,
and I can have different alerts or errors that when this breaks, I can send an email or I can ask it to do a certain action. And so this is the properties now. And now if I click properties in JavaScript, now I can actually start running, writing some code here that will be my JavaScript parser. And so that I can use that as a simple transformation layer. And then finally, I can actually start doing other options. And so I can do this in a batch setting. I can also do this as a sync. So syncs are basically, I take my source data, I transform it, and the sync is going to actually receive tables data. So here I'm going to click BigQuery again. And so now you can see it's a sync. You can tell it's a sync because it's purple. The green is also going to be our source. And so now we've got our JavaScript code. It's running this transformation, and it's going to move any data set from our table in BigQuery, transform it, and load it into another system. So I can give it a property as well. If I click on properties, I can again give it a data project ID that I want it to send to. I can then also provide a table and a data set that it should go to, and I can ask it to validate those settings for me. And so this is just a very basic pipeline where we have our extraction, our transformation, and our loading step. So this is our ETL. And now what I can do is I can actually click save up at the very top after I've named my pipeline. So I'm going to give it my example pipeline. And it's all, as you can tell, it's all very low code, but there's also spaces where I can actually have good code. Like JavaScript here, I can write my own code to do it, or I can use any other transformation layer, a script that they have, such as a field compressor or transpose, or basically some type of basic transformation, such as a CSV parser. I can have that in place here, and I can use it to do some transformation. Now, if I save it, and then you'll see it's green here, it says my example pipeline has been saved, I can actually deploy this Data Fusion pipeline directly on the instance that I have, and then this will actually run. And that is as simple as that. Another thing that I can do is I can actually schedule this pipeline so that it runs on a certain day. So every day it'll run at 1 a.m., for example. And so this pipeline is scheduled to run every day at 1 a.m. Maybe I want this to run weekly, and I could say every Sunday at 1 a.m. And then max occurrent runs is I can have it maybe run 10 times. It can run 10 times at the same time if I want to. So it's the number of concurrent runs that I can control. Once I have that ready, I can save that schedule, and then I can deploy it. I can also import and export these pipelines, and export this pipeline itself so that another user on my account in my organization can use this. And I can also even import their own pipelines if they have one created, and I can deploy it onto the system as well. And that is just a very basic cloud data fusion system that we can create. And I encourage you to go ahead and try out some of the low-code transformations for different use cases that you may have. And then that's it. That's how you can actually deploy your code and run it on Data Fusion. In this video, we're going to identify the choices that affect the cost of Dataproc, Dataflow, Dataprep, and Data Fusion. Let's first start with Dataproc pricing. Dataproc pricing consists of two parts. There's Dataproc on the compute engine, and there's Dataproc, a little more robustness, called the Google Kubernetes engine. This GKE is used for horizontally scaling our machines, and when VMs are added to the cluster, those machines are charged for the period of time that they are active. And we'll add machines to the cluster and remove machines to the cluster based on the traffic that we're working with. Now, with an on-compute engine pricing model, we're basing it on a fixed size of Dataproc clusters with no scaling and the duration of time that they run. So the size of a cluster is based on the aggregate number of virtual CPUs across the entire clusters. You could have 4 or 5 nodes in that cluster, each with a certain number of CPUs or virtual CPUs, and you add up all of the CPUs across all of those nodes to get us the virtual size, and we're going to be charged based on that total number of CPUs per hour. So it's 1 penny multiplied by the number of virtual CPUs times its hourly duration, and that's typically what we're working with here. So we're basically being charged for the time that we're using these compute engines, both in the on-compute engine or the Google Kubernetes engine. Keep in mind that the Google Kubernetes engine is also using virtual machines as their nodes, and they're just a little more fluid. So you could have 5 virtual machines during low traffic and 10 virtual machines during high traffic. And so the total is going to be the times that you're using those number of machines. Okay, so Dataproc serverless pricing matters here when it comes to data compute units, or DCUs. So DCU rate is going to be based on an hourly rate, and it's prorated and billed per second with a 1-minute minimum charge if standard shuffle is used and a 5-minute minimum charge if premium shuffle storage is used. So depending on that, now you could be paying up to 7 cents per hour and US dollars, depending on the region that you're working with. And different regions will cost a different amount of money. And there's also shuffle storage pricing, and there's also a different rate for that. That also matters. Again, it's based on either 5 cents per gigabyte or 13 cents per gigabyte, depending on where your regions are. You have accelerator pricing. So the accelerator rate is what's shown below. What you'll talk about here is this is the tool that's actually used to help speed up the processing when it starts to be bogged down. It's prorated and billed on a per second basis, 5-minute minimum charge. And so depending on your cost, you could be paying $4.60 per hour for an A140 gigs of data, or you could be paying $6.16 per hour for 80 gig charge, or for 80 gig data in an A100. So it sort of matters exactly where these services are being hosted, and that's really the key here. But you'll get different prices for these accelerators, for the shuffle storage, and the data compute unit pricing. So data flow pricing matters here when we're working with compute resources. So data flow usage is billed for resources that our jobs are going to be using, depending on the pricing model that's being used and the resources that are billed, and they're all billed a little bit differently. So we'll have data flow compute resources. We'll be paying for those. And these can include things like worker CPU and memory for both batch, streaming, and FlexRS. There's data flow shuffle data process, such as batch and FlexRS. And there's things like legacy streaming engine data process, which is just meant for streaming only. Those are going to be they're going to be used. Now there's different data flow prime compute resources that also are billed for. And they could include things like, again, the worker CPU and memory, the data flow shuffle data process for batch workloads. They'll have things like stream engine compute units and stream engine data processed units. Now, the regions and their zones are going to dictate exactly the hourly price for these. And there's also things like other data flow resources, such as not just CPU and memory. You'll have things like your stream engine pricing and your stream engine compute units. Those are all going to be place. And we have non-data flow resources that are also going to cost, and this could include things like networking costs for moving data from one to the other, from one zone to the other, for example. And there's many different types of costs that just are associated with using services in the cloud. And that's when you're moving data across zones, especially, those are all going to play a role in the total cost. Now, data prep exists in 3 editions. We'll have things like Starter, which is best for your ad hoc data preparation to solve complex data problems very quickly. And it's up to 60 automated workflows are enabled. We'll have Professional. This is best to create, automate, and monitor data pipelines definitely for your mission critical business analytics. So it's not for ad hoc data. And it has up to 3,000 automated workflows. And then you'll have the Enterprise plan. This adds programmatic access via your APIs. You can use advanced security, fine-grained access controls, or role-based authentication, so RBAC. So there's the single sign-on, or SSO, that are also available, and it has up to 15,000 automated workflows. So this is meant for your very large enterprise organizations with many users of pretty much whole departments that they should be using. Another thing that we have is data prep pricing. So we've got things like our per user fee. And this is the monthly subscription fee based on the edition we're going to be choosing. We've got things like our platform fee, which is paid at the organization level. Could be granting the ability to create or provisioned environments for a dedicated set of users. There's an onboarding services that are available. This is just a one-time fee for product setup and guidance. And there's things like workflow packs. This is open so that you could purchase packs of about 6,000 additional automated workflows if you need them. And this is meant for the professional and enterprise edition. Let's talk a little bit about Data Fusion and Data Fusion editions here. We've got the development. And so this is, again, the developer is going to be paying for certain editions for this. And again, you're going to be paying for the number of minutes between the time a Cloud Data Fusion instance is created to the time it is deleted. So the rate for pricing is going to be defined on the hour, but Cloud Data Fusion is going to be billed by the minute. And so depending on what edition you're going to be using, you'll have different settings for it. So 35 cents per minute is about $250 per month for the developer. You've got things like your basic, which is $1.80 per minute, which is about $1,100 per month approximately, and $4.20 per minute for the enterprise, which is about $3,000 per month. And you'll notice is that the basic edition will offer the first 120 hours per month per account free, which is useful. Keep in mind, though, that all of my prices are for the US East 2, and they are for US dollars as well. Now, Data Fusion pricing, it's not just the edition that we have to worry about, but it's also the using other Google Cloud resources that we could be working on, such as Dataproc, cloud storage, even networking and BigQuery costs. And so if you're building replication jobs, BigQuery has the flat rate pricing, which is recommended for this, not on-demand pricing that you should be using. There's also different supported regions. Cloud Data Fusion is the same for all supported regions, but they have different costs associated with them. So you'll have to look online to see exactly what those cost numbers are going to be for Data Fusion, but it's going to be dependent also on zone and where you're going to be hosting these services. So that's a little bit about the different pricing for the data products in Google Cloud.
In this video, we're going to identify some common issues that can arise with Dataproc and how to troubleshoot them. Let's first start with using open source web interfaces in Dataproc. Now, what this means is that we get to use them to monitor cluster resources and job performance, and there's actually going to be a fully managed, highly scalable service for us to actually use these open source web interfaces. So they actually offer open source components directly in Dataproc, and you could use things like Apache Hadoop and Apache Spark, and they all provide web interfaces. Now, these interfaces can be used to monitor our cluster resources and even our job performance. So if I want to use the Yarn Resource Manager UI to view Yarn application resources that are actually allocated on a Dataproc cluster, I can do that. And this allows me to create a persistent history server to retrieve data for after cluster deletion. So what this means is that when they terminate, you delete the cluster, and so to view cluster and job data after a cluster is deleted, I can use this persistent history server. So if I encounter a job error or some slowdown that I want to analyze, I can just stop or delete the job cluster. Then I can analyze the job history inside of this server. So there's also logging that's very useful to actually identify some of these errors. So Dataproc logs are going to be collected and generated by things like Apache Hadoop, Spark, Hive, and Zookeeper, and really any other open source systems that are running on our clusters. And they're going to send these things directly to our logs. These logs are going to be grouped based on the source of the logs, whether they're coming from Hadoop or Spark or Hive. And this allows us to select and view our logs of interest. And now what we can do, for example, if I had like Yarn Node Manager and Spark Executor logs, they're going to be generated on our cluster and they're going to be labeled separately so that I can use them. This is where we'll use things like cloud logging. Now, this is just a fully managed real-time log management systems, so it provides storage for logs ingested from Google Cloud services such as Dataproc. In there, we'll have tools to search, filter, and analyze logs at scale. And so these clusters are going to generate multiple logs, including Dataproc logs and cluster startup logs, and as well as Yarn Node Manager logs, etc., whatever open source tools we have. And with logging enabled by default on these clusters, we can actually use these things in the Google Cloud Console to actually navigate those log files that are generated by the cluster. Now, there are certain metrics that are going to be useful. One of them is that there's Dataproc cluster and job metrics that are very simple for us to use. So they're prefixed with dataproc.googleapis.com/, and those are how you know that those are actual metrics that are on the cluster and the job. And they're going to consist of things like time series data, and they're going to provide insights into the performance of our cluster, such as our CPU utilization or our memory usage or some type of job status.
We'll also have some Dataproc custom metrics that we can actually create, and they're going to be called custom.googleapis.com. That's what they're going to be prefixed in our log files. And these will include metrics that are emitted by our open source systems that are running on the cluster, such as Yarn, for example. And this allows us to gain insight into Dataproc metrics, and it can just help us configure our clusters efficiently once we can actually use logging to search them and monitor them. Speaking of monitoring, we have things like cloud monitoring, which will allow us to use clusters, metadata, and metrics. And so monitoring is going to use this metric, including things like Yarn or job and operation metrics to provide visibility into the health, performance, and even the availability and visibility of our clusters and our jobs. And monitoring is going to allow us to explore these metrics, and we can even add charts, build dashboards. I can even create alerts for when certain errors start to come. Cloud monitoring as well comes in place when we have things such as our Metrics Explorer. Now, what this is, it allows us to use this to view our Dataproc metrics, and so our cluster, job, and serverless batch metrics are going to be listed inside of this Metrics Explorer. And we can actually go ahead and create charts here. We can use Metrics Explorer to create charts, and it'll allow us to visualize these same Dataproc metrics that are listed there. Another thing with cloud monitoring is the fact that, yes, dashboards are going to be built, and we can build our own dashboards to monitor the metrics that we deem useful for our use case. And so not only can we build these dashboards, but we also have alerting systems in place. So when a certain value is reached on one of the metrics and that we need to be alerted to actually respond to it, we'll get an email or some type of text message or some way for us to alert, either via Slack channel, for example, to receive timely notice of these cluster or job issues that we set with our Metrics Explorer page. And that is a little bit on troubleshooting when it comes to Dataproc. In this video, we're going to identify some common issues that can arise when working with data flow and how we can troubleshoot them. So when we're actually troubleshooting data flows, we want to make sure that typically what's happening is we have to make sure that we're using our pipeline best practices. So some best practices for our pipelines is for batch jobs. We recommend that you use like a time to live for the temporary location of the batch job. Or before setting up this time to live, and as a general best practice, you want to make sure that you have staging locations and the temporary locations to different locations in our pipeline. You don't want to delete objects in the staging location. And if a job completes or is stopped and the temporary objects are not cleaned up, make sure to manually remove these files from the cloud storage bucket that is used as temporary location. And you also want to make sure that you check your pipeline status. And this can be done very easily in the Google Cloud Console. If you go under Big Data and click Data Flow, you'll see that there's an actual status field for all of our jobs. And you want to make sure that they're either running, succeeded, or failed, and you get to see exactly why they are failing in that window. And so now you've noticed something is failing, you want to make sure that you're gathering information about our pipeline failures. So this is where we're going to be reviewing our job error messages. You can view the job logs, the worker logs, the diagnostics, and even the recommendations tabs. They'll all have pieces of information that will help you troubleshoot this information. And you get to even look at these view step logs. So when you select a step in your pipeline graph, the logs will then panel and show you exactly what's happening at that step, the log specifically for that step. So you get to see if everything is working. So you can actually visually inspect this pipeline in the GUI. And some common causes of pipeline failures that I've seen is called graph or pipeline construction errors. These are errors that occur when data flow runs into a problem, either just building the graph of steps that compose your pipeline. And this is what's described by your Apache Beam pipeline. You've got things like errors in job validation. So you've got the data flow service validates any pipeline job that you launch. So any errors in that validation process can prevent your job from being successfully created or even executed. You'll have exceptions in our worker code. Now, these are errors that are occurring, bugs in the user-provided code that data flow is distributing to all the parallel workers. This is more like there's a problem in your code, like there's a runtime error in that code. And there's even other Google Cloud services that can potentially create errors. These are transient failures in those cloud services. So your pipeline might fail because of a temporary outage, for example, or another problem in the Google Cloud services where data flow is dependent on it, such as compute engine or cloud storage. Another thing that you want to do when troubleshooting pipeline failures is go ahead and take a look at detecting of our graph for pipeline construction errors. That's going to be a big one. Look at the logs exactly of what's happening in that pipeline. Another thing that I suggest is try to detect errors in the data flow job validation. So when there is job validation error, take a look at the logs there. Make sure that your services can access your jobs that are associated with your Google Cloud Storage bucket for file staging and temporary output. This could be potentially due to a permissions issue on the service account, so make sure that that's set up properly. There's also detection of exceptions in our worker code. This is important that before you even deploy this to Dataflow, that you have some type of environment for you to test your code before it distributes it to a pipeline that could potentially cost you money. So proper testing procedures on your code locally is what's going to prevent this kind of exception from happening in the cloud. Some typical data flow errors that you could see here. So, when working with data flow errors, you'll get things like missing log files or pipeline errors. Those are the most important ones that you'll see. So those kind of things can actually prevent your data flow from happening. So it's typically with the pipeline that you're going to see some major problems. So in the pipeline creation step is where I've noticed the most problems when creating these. And slow or stuck jobs is another one. So when this happens, this means that the pipeline could potentially is not reading data from the source. So if you have some sort of pub sub that's growing a backlog, the pipeline isn't writing data to the sink. The data freshness metric is increasing and the system latency metric is increasing. These are all reasons for those failures. And so you have to try and diagnose the problem there. And that really just comes down to looking at the logs and why this is not working. It could be a number of reasons, such as trouble for insufficient parallelism. If you don't have enough worker nodes associated to the cluster, that could also create slow or stuck jobs. This just means that you may have to reassess how much computational resources you need to actually finish the job that you're trying to do. That's a little bit of the troubleshooting and considerations when it comes to using Dataflow. So in this course, we've examined how to use Dataproc, Dataprep, Dataflow, and Datafusion to efficiently manage and optimize data pipelines, ensuring a comprehensive understanding of big data processing tools and their cost implications. We did this by exploring comparing Dataproc, Dataprep, Dataflow, and Datafusion, Dataproc cluster options, and creating a cluster and running a Spark job. There's Dataprep flows, profiling, transforming, and sampling data and using Dataprep. And there's Dataflow and building/deploying a Dataflow pipeline and its options. Datafusion, setup and management and creating a Datafusion pipeline, and pricing and troubleshooting Dataproc, Dataprep, and Dataflow. In our next course, we'll move on to explore how to navigate the machine learning landscape, discerning and applying the right systems, tools, and models, including pre-built and custom-trained ones to effectively integrate machine learning into various businesses and data environments. Even with proper care and maintenance, machines like automobiles and planes can have various problems. Repairing those problems is critical since people's lives depend on the machines functioning correctly. Likewise, we need our data warehouse environment to be able to have plenty of gauges and readouts to know how well it's operating. And we need to expect the worst and mitigate disaster by putting strong structures in place that can handle individual failures along the way. In this course, I'll explore the intricacies of troubleshooting and monitoring with Google Cloud Monitoring, where you'll learn to navigate the complexities of cloud performance, delve into the depths of Google Cloud logging to ensure seamless operational flow, uncover the potential of the Google BigQuery admin panel for efficient data analysis and management, discover the art of managing streaming pipelines for resiliency, ensuring robust data processing under varying conditions, learn the strategies for load balancing jobs in multiple locations to optimize performance across global infrastructure. I'll tackle the challenge of handling duplicate data and streaming pipelines with advanced techniques for data integrity, gain expertise in data replication for Cloud SQL, enhancing database reliability and accessibility. Lastly, I'll cover high availability with memory store Redis clusters, ensuring your applications remain highly responsive and resilient.
This course is your gateway to becoming a proficient cloud professional, ready to handle the dynamic demands of modern cloud infrastructures. This course is one of a collection that prepares learners for the Google Professional Data Engineer exam. In this video, we're going to describe the use case for configuring Google Cloud Monitoring to track and troubleshoot within the Google Cloud Platform. Let's first talk about troubleshooting and monitoring that's built inside of Google Cloud Monitoring. So Google Cloud Monitoring is just a service that allows us to monitor or provide insights into the health and performance of all of our Google Cloud services in one location. It automatically collects and stores data for most Google Cloud services by default, and some of them can be enabled. Prometheus metrics can be collected using what's called an ops agent on our virtual machine, so I can actually see what's happening inside of my virtual machine tasks when I use a Prometheus ops agent. Now, the idea is that this data is all going to be referenced back to a singular dashboard. And from this dashboard, I can set up things like alerts and notifications. So I can be notified when the value of a performance metric meets criteria that I can define. And this is where I can have an alerting policy that's in place. Now, the alerting policy will include things like the list of people or groups who are available to receive our notifications. We have proactive monitoring and validation that's also in place. This is where I can test the availability, the consistency and performance of our services, our applications, our web pages, and APIs. And we can create things like our synthetic monitors as well. Now, I can actually probe things like my TCP endpoints, my HTTP or HTTPS endpoints. I can look at things like responsiveness with uptime checks, and I can run these checks almost on a scheduled basis whenever I'm looking to sort of collect some information. And then I can get notified when an endpoint will fail to respond. And then there's things that I can actually trigger when that happens, such as sending out an email notification. Now, one great tool that Google Cloud Monitoring Services will offer is data visualization. So not only do I collect the data, but I can visualize them to see things like trends. I can identify certain outliers, and I can view other details about the data that I have. And there's different charts that I can create directly in that dashboard. Now, the dashboard will automatically create what's called a Google Cloud Managed Dashboard when I add a resource to my Google Cloud project. And then a dashboard will be created, and it will allow me to actually add a graph or take away a graph this way. Now, a great thing is that not only am I visualizing data, but I'm also collecting it and storing it for perhaps a future use case. So maybe I want to be able to do a task that includes things like some type of historic analysis on my API to see how it's performing over a certain month, for example. I can see that there's user-defined metrics that can be created with this cloud monitoring API and actually store them. But it's all available for me to actually store and reference for later use. Now here's some Google Cloud Monitoring data visualization tools that we have. So we've got managed dashboards that are created when you add a resource to your Google Cloud project. Where there's custom dashboards that can be created to display charts, graphs, tables, logs, and error groups all in one location. And there's even a metrics explorer. This allows visualizations of things like time series data, where I can actually start to do some autocorrelation functions or something like that, where I can look at the window of time and see how they're performing over a certain window. Now there's Google Cloud Monitoring data collection and storage. We'll work with system metrics that are generated by other Google Cloud services. And this is just a way for us to see how the service is going to be operating. We've got things like our system and application metrics that the ops agents will collect about the system's resources and applications running on things like our virtual machine instances on Google Cloud. And we can actually see how they're going to perform with Nginx web servers or a MongoDB or a PostgreSQL database that's on the virtual machine. And there's also user-defined metrics as well that I can actually set up. And these can be created using the Cloud Monitoring API, or I can use this library that's called OpenTelemetry that will allow me to create these metrics. External metrics can be defined by some open source libraries and third providers such as OpenTelemetry, and then they can be stored for later use. Now, Google Cloud Monitoring data collection and storage works exactly as you might expect with external metrics, but they also have Prometheus metrics. Now, this is just a tool for us to collect Google Cloud Managed Services using what's called the Ops Agent and the Prometheus Receiver, or OTLP receiver. This is what's actually going to be installed on our compute engines so that we can monitor the services that are running internally on the compute engine, such as Apache or Nginx web servers. And I can generate log-based metrics that could record numeric information about logs. The logs are into cloud locking,
Google-defined log-based metrics will include things like the count of the number of errors, such as a server 500 error, if I'm trying to work with an API, for example, and it'll detect the total number of these log entries received by our Google Cloud project, and then I can actually plot them out or have some type of notification procedure when an event happens. Now, there's actually ways that I can query all of this stored data from Google Cloud Monitoring, and one of the ways is to use a simple Google Cloud Console command. So I can jump on Google Cloud Console and I can build my query by making selections from menus, or I can actually write the query directly in the console where there's a query editor, and we're actually going to be using what's called a Prometheus query language, or called PromQL. And there's also another language called Monitoring Query Language, or MQL, and these query editors will provide things like syntax checks and suggestions, and it's very useful for us to query a certain event that happened in a log stream. Now, there's Cloud Monitoring API that's available for us. The API will support things like I said, PromQL, MQL queries, and these are very similar to the commands that we'll be running in Google Cloud Console, but we are actually doing it directly in an API call rather than going into the console to run those commands. Another great tool for this is called the Large System Monitoring. Now, what we're going to do when we manage resources as a collection with a resource group, so what I want to do is I want to create a resource group, and this means it's going to be a dynamic collection of resources that'll satisfy some type of criteria that I can define. Now, as I add and remove resources, such as adding compute engine virtual machine instances to a Google Cloud project, what will happen is that the membership of the group will automatically change based on what I'm adding and taking away. So compute engine instances whose names will start with a string that I can define, such as prod dash, to signify that these are prod clusters, will now be part of a resource group that I can actually manage or check the logs of that resource group. Or I can actually have a tag attached to the resource group to keep them in the same group. So for example, resources with a certain tag, such as prod, will let me know that any resources that are tagged with prod are part of this resource group, and therefore I can actually monitor that resource group in isolation. This is where I can monitor metrics for multiple Google Cloud projects with a simple metrics scope. And so this is where I can actually leverage the use case of large system monitoring by grouping the resources in one location and then have them show up in a sort of its own dashboard to see how that group of resources is performing. And that is how we can do large system monitoring. That's a little bit about the Google Cloud collection services for our Google Cloud services. And this includes things like alerts and dashboards. In this video, we're going to describe the use case for configuring Google Cloud Monitoring to track and troubleshoot within the Google Cloud logging system. Let's talk about troubleshooting when it comes to monitoring with Google Cloud logging. So what we want to do is we want to be able to collect application and third-party logs that are generated by our services. Now, these logs can be very useful and they can be generated using a client library, but it's not always necessary to use them in our application. So some configurations can use what's called an ops agent to send logs that were written to, say, a standard out or standard error in a Google Cloud virtual machine, for example, and it can pipe those output directly to a system where I can actually troubleshoot and analyze those logs. Now, this system is just going to be a service that's offered by Google, and this is where we'll use Google Cloud Logging for this. And I can view and analyze those log data using the console itself. I can use things such as Logs Explorer or the Logs Analytics pages in the Google Cloud Console. I can query and view these logs with really any interface that I choose. And there's different query languages that are available for those capabilities. So not only I can actually receive that information, but I can actually filter through them with a simple SQL-like programming language to start to query that log file. Now, here's another thing that I can do. I can monitor the system logs. Now, this is where I can get notified when an event appears in an audit log. For example, anytime a user accesses the security key of a service account, well, I can actually have a notification that pops up. Your application could write deployment messages to things like logs, and they could be notified when a deployment change is logged. That kind of thing is useful. Now here's where we can actually do some of the troubleshooting in our analysis. So there's a tool called Logs Explorer, and it can troubleshoot the performance of our applications and services that are running inside of the cloud. Now this is just really useful to create a histogram that displays the rate of errors, for example. If I see a spike in errors or something that is interesting, I can locate and view the corresponding log entries there. So it's a nice way to actually get a 1,000-foot view of my logs that are generated. There's log analytics that can run queries to analyze our log data, so I can actually create maybe some metrics. So if I'm trying to troubleshoot a problem and want to know the average latency for an HTTP request to a specific URL over the last 3 months, I can do that by querying that information. Now there's also Cloud Logging API and Google Cloud CLI that can export our log data for us, and that's always going to be available. So I can take this information and export it to another service, or I can put it in a database, or I can attach it even to a BigQuery table, for example. And so I can then use BigQuery and Google SQL to query that data into a table that I specify. Now, monitoring our system logs just involves doing a few things here. They could involve, for example, cloud monitoring can be used to observe trends in our log files. So I can look at log-based metrics, and then I can also generate some numeric data from this log data, not only just by looking at the graph, but also looking at sort of the average of a certain metric. And this is where I can actually have some type of user-defined log-based metrics collecting data that will be received by the log router from all logs. So I define what metrics I want to work with, and then kind of route them through this log router, and then they'll go into one location that I specify. Now this is where I can have log-based alerting that can send messages when a specific message occurs. So typically what will happen is that there will be some administrators that will get an email when a certain event happens, such as the CPU load on a virtual machine, for example, is too high. We'll get some type of alerting from this log-based alerting system. Now, there's a couple different log types that I want to work with here. One of them is called the user-defined log-based metrics, and this is where they're calculated from all logs received by the logging API for the Google Cloud project. And this is going to have some inclusion filters or exclusion filters, and they may apply to a singular Google Cloud project. Now I can create an alerting policy here based on this user-defined base log metric that I have, and then the policy will monitor the data for all of the logs. Now there's system-defined log-based metric. Now these are calculated only from the logs that have been stored in the buckets in the Google Cloud project. So if a log has been explicitly excluded from our system, then it's not going to be included in this metrics. So if I'm trying to create an alerting policy based on a system-defined log-based metric, then what's happening here is that the policy is just monitoring the data only from the included logs that are inside of a bucket. So they're a little bit different, but log-based alerting policies will operate only on including logs, and you can't use log-based alerting policies to notify about messages in excluded logs. Now, both of these metrics and alerting policies operate on the Google Cloud project level, not on the individual bucket. So it's all over the entire project. Now, here's some Google Cloud log categories as well. So we've got things like our platform logs. Now these are logs written by your Google Cloud services, and they can help you debug and troubleshoot issues, and they can help you better understand the Google Cloud services you're using. We'll also have something known as component logs, and these are similar to platform logs, but they're generated by Google provided software components that will run on our systems. And finally, there's the security logs. Now, what this security log is more trying to figure out not what went wrong, but we're trying to keep track of who did what, where, and when in our Google Cloud project. So this is where they're useful for things like cloud audit logs that could provide information about administrative activities and access within our Google Cloud resources. And then we'll have access transparency, which will provide you with logs of actions taken by Google staff and when they're accessing your Google Cloud content. So this access transparency logs helps us track things like our compliance, and they are great for legal and regulatory requirements for the entire organization. Now there's Google Cloud log categories as well. We've got things like our custom user logs. So this is crucial. And we have the custom user logs for us to actually be able to create logs ourselves. So we define what we want to include in these logs. And we'll have even multi-cloud logs and even hybrid cloud logs. So just like with our custom logs that you see here, I'll have things such as the multi-cloud and hybrid cloud logs so that I'm receiving them from other cloud providers such as Microsoft Azure, or I can have something that's logging from on-premises infrastructure and they'll be stored in the cloud for backup. There's also what you'll notice here with Google Cloud Logging Storage is that there's going to be a cloud logging bucket, and this will provide storage in cloud logging. Now, all this log bucket is going to do is just store our log entries for us, and they could be received by multiple Google Cloud projects in this one location. I can combine my Google Cloud Logging data with the other data by upgrading my log bucket to use what's called a log analytics tool, where I can actually do some querying of the data set. Another thing that I can do is I can update my log analytics. I can create a linked BigQuery data set for this system. And then from this BigQuery data set, I can provide things such as a Google SQL query to analyze my data that I've stored. Now, all of this is going to be done in the cloud storage bucket, and it's the main resource to actually hold all of our logs that we have. And this is going to provide a storage of all of those entries, and they're going to be stored typically as JSON files. And so you can actually view these log entries routed to our cloud storage directly in the Google Cloud Console. Another thing that I'll bring up is this concept known as the pub sub topic. Now, this is going to provide support for third-party integrations. I like to use this so that when log entries are formatted into JSON and they're routed to a pub sub topic, this is where I can have a few different subscribers that are listening to this topic, and they can do a certain action. Another thing that's great is Google has support for a tool known as Splunk. This is where I can route my log entries to a pub sub topic, and then I can subscribe to that topic by using Splunk, and a certain action will take place depending on what I need to do. Now, the Google Cloud project itself will route all log entries to a different Google Cloud project, and when I route those log entries to a different project, the destination project's log router will receive them, and then it'll process them and either store them in its own bucket or in a separate bucket. This is going to be our sink, basically. That project is going to act as a sink for all of those logs. And there's even other resources that we can do. So I can route all of my log entries to supported destinations that could be in a completely different project. And so those are a little more advanced and tricky, but just know that what we're doing here is just kind of scratching the surface of what's available to actually handle logs in Google Cloud. That's a little bit on log storage when it comes to Google Cloud. In this video, we're going to describe the use case for configuring Google Cloud Monitoring to track and troubleshoot within the Google BigQuery administrative interface. Let's first get started with understanding how troubleshooting and monitoring works within our BigQuery admin panel. Now, we know that Google is going to provide us the capability to audit and monitor our resources, including BigQuery tables. Now, how does this work is that we have the cloud monitoring for a dashboard that's solely dedicated to BigQuery. And this is where we can use this dashboard to view information about our BigQuery incidents, our data sets, our tables, our projects, and our query times, as well as slot utilization. There's also things such as the cloud monitoring that allows custom charts for resources and metrics and aggregations, so that I can actually look at all of these logs and create some plots so that I can view them at a high level to see what's happening in my BigQuery system. Now, the capacity management page of the Google Cloud Console can display things like slot usage. And this is where we want to be able to monitor some of our quotas and take a look at if we are over provisioning or under provisioning our system. Now, troubleshooting and monitoring within the Google BigQuery admin panel also involves using set limits on the use of BigQuery resources so that we know that they're using the right usage and protect from runaway costs for our resources, the underlying resources that Google provides. And so I can actually make sure that I'm not going to be running up my bill by setting hard limits on query time, for example, knowing that they can't access a certain query or a certain amount. That's going to prevent the cost from spiking. And there's also going to be cloud audit logs that'll maintain a record of all of our BigQuery events that we've done. Now, from these cloud audit logs, this is where we can use things like Log Explorer to query the logs themselves, and there'll be certain events that are related to BigQuery jobs or data sets or some transfers. And there's actually a logs dashboard that can display information about even the recent errors, and I can use log-based metrics to count those number of log entries that match a given filter. Now, here are some of the metrics in the logs that are available. So I can monitor and log vary based on sampling frequency. And there's going to be metrics are collected regularly for our analysis. And you'll also notice that the logging entries are created for new tables, and they could also be created for purchasing slots and running load jobs. Now, this is where monitoring and logging sources can vary based on the frequency of sampling or aggregation. It's important to keep in mind that as we're collecting this information regularly for our analysis, we are going to have different ways for us to grab some statistics on the system that we've collected. Now, they're all going to be varying in time frames. So as we're going to look at the frequency of how many times something is going to be logged. Maybe it's going to be logged every couple of seconds, every couple of minutes, every couple of hours. That's all going to vary depending on how we're going to start collecting some statistics on those logs. Now, we want to be able to monitor the real-time health of BigQuery. And so this is where BigQuery operational health monitoring is a centralized monitoring system. And it lets us observe the usage of BigQuery across the organization and multiple locations. And we can view administrative resources utilization. So primary use cases for this is that we can identify the root cause analysis for capacity planning based on some of the historical resource utility that we've had. And we can diagnose some performance changes in our system as well. I can also view Administrative Job Explorer. This is still in a preview state, but you can actually filter your jobs and view execution details, and you can get insights for your queries based off this Explorer. Here's a couple more BigQuery monitoring features that I want to mention. So one of them is that BigQuery Data Transfer Service will monitor and log workloads performance for us. And materialized views usage is available in the BigQuery information schema view. So that's very useful for us if we're working with materialized views. And BigQuery reservations are viewable by the BigQuery administrator. And you'll also notice that there's going to be continuous queries that are monitored by using the information schema views that are built into the BigQuery. So I can actually see how these queries are performing. Here's a few more of these monitoring features that I want to talk about that are built into BigQuery. So one of them is we can use the BigQuery Analytics Hub to view usage metrics for data exchanges between two data sets. We can actually look at cloud monitoring that can be used to monitor and troubleshoot, say, a business intelligence engine usage. It's all built into BigQuery. And so this will work with different cloud services to monitor this engine. So if you're using Looker Studio with BigQuery BI engine, this is all supported, and I can actually identify how it's going to, if there's any problems with BigQuery and the Looker Studio connection there. And there's going to be Cloud Dataplex API. This can be used to define continuous data, and this is where I can actually check for continuous results, monitor my results, and troubleshoot some issues that will all be there as well. Here's some concepts that I want to bring up on BigQuery quotas and our limits. So quotas will monitor the consumption of Google Cloud services and our products. They can also restrict the usage of resources to reduce spikes and ensure fairness. Quota restrictions are automatically enforced, so I can actually maintain configurations that'll enforce my prescribed restrictions that I have, and quota changes can be requested if need be. So I can actually contact my administrator and take a look at changing my quotas for my system, for my BigQuery system. So that is the idea of how we can use BigQuery to monitor and log the system, but also there's ways that there's some limits and quotas that we can monitor and change ourselves, and they just prevent us from running up the bill. So that's a little bit on how BigQuery and logging works. In this video, we're going to describe the behaviors of updating and restarting jobs when we're using Google Cloud Dataflow. So Dataflow is just a data pipeline model. It's where data will move through a series of stages that we define, and they can include things like reading data from a source, and that source could be a stream or a file, and we can transform and aggregate the data and then write them to a destination, which could be a BigQuery table, another database, a NoSQL table, something like that. This is the idea of using data pipelines to move our data through our stages. And like I said, these stages are going to include things like reading and transforming and aggregating our data. And you'll notice that Dataflow can be used with things like Apache Beam pipelines as well. And it'll allow us to allocate a pool of virtual machines to actually execute these pipelines so that we can transform and aggregate our system. Now, there's some advantages with using Google Cloud Dataflow. One of them is that this is a fully managed service, so we don't actually have to worry about any of the underlying infrastructure. Google is going to manage all of that for us. And in this way, it becomes very flexible for either small, medium, or large jobs. Google Dataflow will handle all of that for us.
And it actually supports batch and streaming pipelines, even at large scales. So whether I'm doing things on a timer, so every hour retrieve data from the source, or I have records flowing through a pipeline, through a stream, for example, and I can actually transform that record coming through that stream as it comes. And it doesn't matter what scale we're at here. So Google Cloud Dataflow is going to be built on the open source Apache Beam project, and it can be used for simple or very complex projects thanks to its natural scaling. And Dataflow jobs can be monitored, and they're completely observable for us. So this is where we can use the Dataflow monitoring interface in the Google Cloud Console to take a look at the status of our pipeline. Now, the interface will include things like a graphical representation of the pipeline, and it can show us the progress and execution details of every stage within the pipeline, whether that's extraction, transformation, or loading. And the monitoring interface will make it easier to spot our problems, such as bottlenecks within our pipeline, or if there's high latency somewhere, it'll start to pop up on our dashboard there. Here's a basic use case for Dataflow. We've got things as Dataflow is for data movement, so it can actually be unified stream and batch processing. So it's just moving that information. It's primarily used for ETL workflows where we're going to extract or ingest that data and then transform and load it into a data warehouse such as BigQuery. It's utilizing Power BI dashboards as well, so I can actually create my own dashboards with the data that I've collected, and I can even apply machine learning in real time to stream the data. Now I can actually have processing sensor data or log data in place, and Dataflow will use the same programming model for both batch and stream analytics. And this is where I can actually have my sensor data or my log data going into a cloud logger, for example, and kind of have it taken to do a dashboard and see how the system is performing from those logs. I can actually upgrade my streaming pipeline directly. So I'll have like in-flight updates that can be performed without stopping the job completely. So I can see some ongoing streaming pipelines without stopping the entire pipeline, and we call this an in-flight job update. And now what this means is that the job must be using a stream engine, and it must be in the running state for this to be in flight. So without stopping anything, I can update the pipeline to make it change its behavior just slightly. And so launching a replacement job may cause some downtime. So if the updated job is compatible with the existing job, I can even update the pipeline by using this very basic update option. But if I replace an existing job, what will happen is I have to tear down the old job and bring up the new job. And that kind of deployment is going to cause some data loss. So I can actually run parallel pipelines to avoid disrupting an existing pipeline as well. So what I like to do is I'll create a new streaming job that has the updated pipeline code and run the new pipeline in parallel with the existing pipeline. Then it's basically almost like a blue-green deployment. I'll move data from the old one and point it to the new one, and then once no data is in the old pipeline, I can actually tear it down. So the parallel pipeline limitations that I talk about here is that the downstream system needs to compensate for any duplicate data. As we know, like going to be having two pipelines working simultaneously, an updated one and an old one, and they're going to be processing the same data. And so we have to be able to make sure that the data store is going to be able to tolerate duplicate data. And we have to use the same subscription for multiple pipelines. It isn't recommended when reading from a pub sub source. So you want to have a different subscription for each pipeline that you're running. And another thing that I'll bring up is that duplicate data is going to be generated, but data correctness and auto-scaling will work correctly, even if you do have a parallel pipeline limitations. That's a little bit on how Dataflow works, how the pipelines are structured, and just how logging is going to be collected from those pipelines and then stored in a location for us to view later on to make sure that our pipeline is behaving appropriately. In this video, I'm going to identify some of the steps that we can use to understand our traffic and our networking inside of Google Cloud. Let's go ahead and take a look at the Google Cloud load balancers and what they are. So what load balancing means is that it's just a way for us to distribute traffic across multiple instances of our applications. I can spread the load, or what's called load balancing, which makes sure that we can reduce the risk that our application will experience some performance issues. What this means is that I can actually use what's called a single anycast IP address. So this means that
Single Anycast IP address is acting as our front end for all of our back-end instances in regions around the world. So if I want to access my back-end, I don't have to access the individual IP addresses of the machines. What I can do is I can actually access the IP address of the load balancer, and the load balancer can then forward the traffic over to one of the servers. And this means that we're going to have auto scaling. Now, the interesting thing about a load balancer is that it's going to understand which machine is going to get the traffic routed to it. So it's going to figure out what machine to send the information to, my request to, based on the load of the machine. So this is where, as I have a lot of users and my traffic's starting to grow, there's going to be approximately an even amount of traffic on each of the servers that are attached to the load balancer to make sure that things are being balanced and that not one machine is bottlenecking the whole application. And so this is what's known as software-defined load balancing. So because it's a fully distributed software-defined managed service for all of our traffic. Now, we also can get Google Cloud load balancer features. So we'll have things like layer 4 and layer 7 load balancing. Now, what this means is that I can use layer 4 base load balancing to direct traffic based on data from a network and some of the transport layer protocols, such as TCP, UDP. So based on what protocol I'm using, I can actually route traffic that way. And I can use layer 7 base load balancing to add request routing decisions based on attributes, such as the HTTP header and the API requests that I'm sending. And so there's an external and internal load balancing that is done. So with this external and internal load balancing, you'll see that you can use external load balancing when your users are reaching your applications from the internet. And I can even use internal load balancing. So when clients within my Google Cloud ecosystem is trying to access the service, they're trying to access the load balancer, then this is called internal load balancing. And there's also going to be a global and regional load balancing as well. So it doesn't matter exactly where you are in the world. You can distribute your load balance resources in single or multiple regions, and I can have them terminate connections close to our users to meet them in high availability requirements if I need to. And there's advanced feature support that's also available that goes beyond load balancing. So we've got things like IPv6 load balancing, source IP-based traffic, wait load balancing, WebSockets. There's even user-defined request headers that can be used. These are all available directly in the Google Cloud Load Balancer. Now, here's some application load balancers that I want to discuss. So there's external and internal. I've kind of mentioned these just a moment ago, but just so you know, external application load balancers are just implemented as managed services, either on a Google front-end service or what's known as an envoy proxy. These load balancers are great for receiving internet traffic from our users and then routing them to a machine. So this is really important for when it comes to application load balancers. So we can use the open source envoy proxy, for example, to enable advanced traffic management capabilities. You'll have a classic application load balancers, which are basically the ones that we think of when we deal with load balancers, is that we're fielding requests from our customers and routing them to one of the machines in a region somewhere in the world. So this is all done through external because it's facing the outside of the cloud. So we call those external. It's basically retrieve traffic from the internet. And then an internal application load balancers is receiving internet from within the cloud. So this is where another service is trying to access another service. And so there might be a load balancer there to make sure that the machine is not getting overloaded. And we also have something known as network load balancers. So these, again, are layer 4 load balancers, and they can handle TCP, UDP, or any other IP protocol traffic. So these are external proxy network load balancers themselves. So what this means is that we're going to distribute TCP traffic to a virtual machine instance in our Google Cloud VPC network, and then we can actually retrieve that information and send it to the right machine for us. Now, you'll also notice is that there's an internal proxy network load balancer as well. Again, this is where we're trying to look at our tools for our internet balancers and make sure that the internal network is not getting overloaded on a particular service. So the load balancer could sit in front of a service, and there's an internal service that needs to retrieve that information. This is called an internal proxy network load balancer, because what's going to happen is it's looking at an internal service and it's trying to serve an internal service with the load balancer. If you have a service that's inside of your cloud trying to access another service inside of the cloud, we call this an internal. And if we have a service that's outside of the cloud, such as a user trying to access a service inside of the cloud, we call those an external facing proxy network load balancer. Now we have pass-through network load balancers. Now these are layer 4 regional pass-through. So this is essentially what this means is that they're going to be built on what's called a maglev. This means that clients can connect to these load balancers from anywhere on the internet, regardless of their network service. And the load balancer can receive traffic from Google Cloud virtual machines with external IP addresses, or from Google Cloud VMs that can have internet access. And you'll have internal pass-through network load balancers, and they are built on a different type of stack. And so what this means is that this network load balancer will let us load balance TCP UDP traffic from behind an internal load balancing IP address. And it's only accessible to systems in the same VPC network or systems connected to our VPC network. This load balancer is configurable on Google Cloud, and it's useful for receiving traffic from within the cloud. Now, regions and zones plays a role here. So remember, regions are just a collection of zones, and zones are deployment areas within a region. So for high availability, it's recommended to deploy our applications across multiple zones and multiple regions, and our load balancer is going to be attached to each of these regions to make sure that these things are going to be evenly distributed for our users. So load balancing jobs in multiple locations kind of works in a little bit of ways. So we've got a global external application load balancer. Now, this is just a load balancer that is implemented as a managed service, uses an open source proxy to support advanced traffic management capabilities. And it has things such as traffic mirroring, weight-based traffic splitting. We have request response-based header transformations and more. We'll also have classic application load balancer. This is the external application load balancer that is used in the Google Cloud. And this is configurable to be regional and standard tier. And so this load balancer is implemented in a Google front-end service, and they are distributed globally and operate together using the global network and the control pane on the console. You'll also have a regional external application load balancer, and this is just a balancer that is implemented as, again, a managed service, and it uses advanced traffic management capabilities. And it's very useful for exactly routing traffic between regions to make sure that each region is getting an even number of traffic. So keeping things balanced across regions, I'd use a regional external application load balancer as well. So that's a little bit about load balancing jobs in Google Cloud and what they can be used for.
In this video, I'm going to describe how duplicate data can arise and how we can resolve this issue. So let's first understand what duplicate data and some of the origins and how they can be handled by Dataflow, because some of them can be handled by Dataflow themselves. So really what's happening is Dataflow is going to be reading from PubSub topics, and we're going to be publishing messages to a particular topic through some type of source or an IoT device. And there are going to be times when this IoT device is going to send a duplicate message in this topic. The subscriber is going to be receiving data, and it's going to be processed by data in Dataflow. Now, it's just going to be listening for any topic and any messages that come to that topic. What happens next is that we're going to be reading from our PubSub duplicates. And it's quite simple, because what will happen here is that PubSub is going to guarantee at least one delivery for every subscription. See, what'll end up happening with PubSub is that, this is a key word here, is at least one delivery for every description. It means that a message may be delivered more than once by the same subscription if PubSub doesn't receive acknowledgement within an acknowledgement deadline. So there's going to be a certain amount of time that's attached to the message that the subscriber needs to be able to acknowledge that it received it. Otherwise, what PubSub will think is that, oh, you haven't received the message, and it'll try to send it to you again. Now, PubSub will deliver each message with a unique message ID, thankfully. So what this means is that I can use this message ID to identify all duplicate messages. So I can log it somewhere, or I can ask Dataflow to filter out these duplicates based on the unique ID. Now, what happens then if I ask Dataflow to filter out duplicates based on the unique ID, I'm only going to be getting unique messages. And so that is going to prevent any type of duplication that I will be seeing in Dataflow. Now, Dataflow is going to process duplicates in a couple different ways.
So each message can be retried numerous times on different data flow workers. This is just the nature of the distributed nature of processing when it comes to data flow. Now, it's going to ensure that only one of those tries will win, and the processing from the other tries of our workers is not going to affect any downstream stages in our data processing. Now, data flow does guarantee exactly once processing is done by leveraging checkpointing at each stage to ensure that each duplicates are not reprocessed that could affect any state or our output. Now, there's certain situations where data flow is great. It can handle some of the duplicates, but there's other situations where the developers need to handle the duplicates themselves. And one of them is that the duplicates could be generated at the source. Another one is going to be publisher could be generating duplicates themselves, or we could be writing to a sink that includes duplicates there. And so there's ways that we can handle these systems. So one is, let's start with identifying the duplicates that are generated at the source. So if your source data system, it could produce duplicate data. So think like an IoT device. There could be several reasons, like network failure for my IoT device. There could be a system error, a malfunction, something like that. And I could send duplicates. And so we refer to them as source-generated duplicates. And what you'll notice is that if you think of a simple example is setting the Google Cloud Storage trigger notifications to PubSub in response to object bucket changes. Let's say I have this set up and I change an object. Well, what will happen is that there might be a situation where this Google Cloud Storage trigger is going to send multiple events to this PubSub topic. And they're going to be for the same object that I've changed. And so this is where you'll notice is that there's a feature that guarantees at least once delivery to PubSub, and it can produce duplicate notifications. So that's a possibility that can be done in the cloud without the use of an IoT device. Now, there's also some publisher-generated duplicates that we need to look out for. So one of them is that PubSub can generate duplicates due to at least once publishing guarantee. Like I was mentioning before, there's an at least once, and that means it could be more than one. And so PubSub could automatically assign a unique message ID to each successfully published message. And then from there, we can use this to identify all of the messages that are duplicated if they have the same message ID. Now, the same message payload may be retried by the publisher, which can cause duplicates, and this is where we need to filter our queues so that we only get the unique message IDs, or we have some type of log in our system so that we can easily check to see if this message ID has been processed. Something like that is what we could do, kind of have some type of tolerance for duplication. Now, how do we deal with this when writing to a sink duplicates? So let's say that data flow workers may retry multiple times and produce duplicate writes. And this is the responsibility of the sink to detect these duplicates and handle them accordingly. Now, this all depends on what our sink is. Duplicates can be filtered out. We could overwrite them, or they could just appear as duplicates if that's fine for us. But if we're dealing with, let's say, duplicates may be filtered out or overwritten, as you can see here, but we can also have files that could get overwritten completely. And so if you are writing files, exactly once is guaranteed, as any retries by data flow workers in event of failure will overwrite the file. So that's the key catch here. So because think of my sink as just a bucket, and I'm getting data flow to generate some files. Now, what will happen is data flow will generate those files and store them in the bucket location. If I receive some type of duplication from somewhere, and because I'm creating a file, due to the nature of the file system in a bucket, I would just recreate that file and overwrite it with the same exact file. So in that situation, when dealing with files, it's exactly once is guaranteed in that case, because no matter how many times I reprocess that message, I'm still going to end up with the same exact file in the system. So that is what's going to make sure that we have that exactly once. So it's not that the data flow is not processing the message only once, it's actually processing the message multiple times, but the byproduct of the file system makes sure that there's only going to be one file. You can't have more than one file with the same name, same object key in a bucket. So handling duplicates in data in streaming pipelines is a little bit different. So we want to make use of the PubSub message attributes that are built into this. And so these message topics can have some string key value pairs attached to it as metadata. And there's a key there that's called attributes of the PubSub message. Now, these attributes are set when publishing to PubSub. So if I'm using Python's PubSub client library, I can set the attributes, a parameter of the publish method when publishing messages. This way I know exactly where the messages are coming from. And so I can set the unique fields such as event ID from your message as an attribute value and field name as an attribute key, so stuff like that. So that's what I encourage you to do when dealing with streaming pipelines. We can also
Make use of the Apache Beam deduplicate p transform.
So Apache Beam provides deduplicate transforms, which can deduplicate incoming messages over a certain time duration. And this can be based on the message or a key of a key value pair, where the key could be derived from the message fields. So that's one way to handle that. Another way is to perform the post-processing data in the sink, which is it's a little more computationally expensive because what we're doing here is running a scheduled job that periodically deduplicates rows using a unique identifier. And so this could depend on what our sink is. If we're running BigQuery in our pipeline, we could have a scheduled query that can be executed periodically that writes the deduplicated data to another table or updates the existing table, that kind of thing. So that's a little bit on how we can use deduplication steps and working with PubSub, with Dataflow, and other Google Cloud services.
In this video, I'm going to identify some of the options of replicating Cloud SQL data. So data replication for Cloud SQL involves a few different ways that we can do this, but there's steps that we have to follow. But just as a broad view, when we're talking about replicating a Cloud SQL instance, what we're talking about is creating copies of a Cloud SQL instance or an on-premises database. And we want to offload work to those copies. So the reason why we would do this, the primary reason for replication is usually just to scale the use of our data in our database without degrading any performance. And so we want to be able to also migrate data between regions. So creating a replicant of the database in another region and then moving data to that region is really important. And we can also migrate data even between different platforms. Another reason is that I could also migrate data from an on-premises database to Cloud SQL in the cloud. And so you can also take the replica that could be promoted if the original instance becomes corrupted. So it's almost a way for us to have fault tolerance by having this. And so there's a few different types of Cloud SQL replication types. So there's read replicas, which is exactly what you would expect. It's a way for us just to read data, not write data. So it's a way to scale our read operations. We can also have cross-region read replicas. And this means that we can have data stored in multiple regions and we can read them depending on what database is going to be closest to the user that's actually querying the information. And I can also have cascading read replicas, and I could also look at external read replicas as well, where there's something external to the cloud. And I can have in Cloud SQL replicas when replicating from an external server, such as the ones that I see on database management system, on-premises management system. Now, this is great when you have these replicas and they're only meant for reading. But let's say that something happens to our original copy, our original database, which is used for reading and writing. Well, what happens is in a disaster scenario, I can promote the read replica and convert it to the original, or what's called the primary instance, where now it's not just doing reads, but it's also doing writes. This way I can use it in place of an instance that's in a region that's having an outage, and I can also promote a replica to replace an instance that's corrupted. And so that's the reason why I would have so many of these read replicas, maybe all over the globe in multiple regions. Now, when we're talking about Cloud SQL read replicas, what we're doing here is we're offloading our work from a Cloud SQL instance. So the read replica is just an exact copy of the primary instance. And so data and other changes on the primary instance are updated in real time on the read replica. And we see that read replicas can only be used for data reads, not for writes. And we also have high availability that could be put read replicas in a different zone. So this is exactly why I would have these read replicas, so that if I want to be able to scale my read operations for my users, putting them in a different zone so that they can access the zone that's the most closest to them is going to give them less latency, and the data is going to get a better user experience this way. So Cloud SQL cross-region read replicas, this is so that we can create a read replica in a different region from the primary instance. So this cross-region read replica is just the same as an in-region replica, except it's a completely different region than the primary instance. Reads can be performed closer to the application's region, which means that we're going to get less latency. Provides a recovery support by being in a different region. So this is the idea of not putting all our eggs in one basket, or all of our database instances in one region, because if one region goes down, all of our data operations cease to exist. But by putting them in different regions, I can have that kind of recovery support so that not all of the regions are going to be affected at the same time, and I can still have a database up and running so my application can live. And I can also migrate data from one region to another, and that's what's actually happening inside of this cross-region read replicas. Now, I'm going to talk a little bit about Cloud SQL cascading read replicas. So a read replica can be promoted to the primary instance. And so this is great for things such as disaster recovery. It can increase the performance of the primary instance as well. So what it does is it's reducing the burden on the primary instance, and it's offloading replication work to multiple read replicas. So it's quite useful for that. Another thing that we can do is we can have multiple read replicas, and they can be used to scale and improve read performance. So we'll have a scalable read operation. So if my application is read heavy, having a cascading read replica is a good idea. And then networking costs. So I can reduce networking costs by using a single cascading replica with cross-region application in other regions. And this is a way for me to actually use these cascading read replicas. Let's talk a little bit about external read replicas restrictions and what these things are. So external read replicas, think of them as just external MySQL instances that can replicate from a Cloud SQL primary instance. And what this means is that I can actually do this even with another cloud platform where it might not be possible. So if I replicate to a MySQL instance hosted by another cloud platform, it's going to be a little bit harder for me to do. But the application may fall behind the primary database if interrupted. So replicating to a MySQL instance hosted by another platform is not possible. Well, what I can do is I can set the configuration field to replicate where a flag is required. And so what cloud providers are going to do is they're going to have a way for me to connect this Cloud SQL replica to an external cloud vendor. But in events that it's not, you'll have to read the documentation of the external cloud provider, whether that's AWS or Azure. But if replication is interrupted, let's say that you can do this for a few hours, you're going to notice is that the replication may fall behind the primary database. It's interrupted, so you're going to have some data out of sync issues. So the replica will catch up once it reconnects to the primary, and it starts replicating again. But if it's interrupted for longer than the replication logs are preserved, which is usually a few hours, you must delete the replica and you'll just have to start a new one. And so that length of time can be configured in your Cloud SQL configuration. So data flow from the primary to the external replica is charged as outbound data transfer, so it's going to increase your data costs as well. So these are just some of the external read replicas restrictions. Cloud SQL replicas from an external server is important here. So this is where we can migrate from an external SQL database directly to Cloud SQL. So if you have an on-premises system, this is where you can actually take your self-managed MySQL server and put this into Google Cloud with very minimal downtime for your application. You can offload database replicas to Google Cloud, and then you can retain colocation and control of your server while you're offloading the administration of the replicas to Cloud SQL. Now, what we'll notice with this configuration is you'll see it sometimes called in the literature a hybrid cloud. This is where your replication between your server and the Cloud SQL replica is going to just continue indefinitely. So you'll have to keep both systems online, the one in the cloud and the one on premises. So that's a little bit about data replication when it comes to Cloud SQL and the different methodologies that are available. In this video, I'm going to describe how high availability for Redis clusters can be created with replicas in memory store. Let's talk about memory store for Redis clusters. So what exactly is this memory store? Well, all it is just a fully managed Redis service, and it's available for us to use on Google Cloud. And what this means is that applications running on Google Cloud can achieve extreme performance
by using this available, highly secure, scalable service without the burden of managing very complicated Redis deployments. So we have these things called hierarchical resource structures. Memory store for Redis clusters uses these hierarchical clusters, and this is just a set of shards that contain primary and replica nodes. And so this is important. If we think of a shard as just like a section of our data, each containing a subset of what's known as our key space, each shard in a memory store cluster is composed of one primary node and two replica nodes. Now, we'll also see that an instance is just a data container. So the terminology for this is a little strange. So for Redis clusters, instance is just a container for our data, and we'll use the terms instance and clusters, and they're sometimes used interchangeably when we're referring to a single memory store for Redis cluster unit of deployment. So when we're provisioning memory store, you have to make sure that you have enough shards to keep your data organized and highly accessible. So all a shard is just a cluster that is composed of multiple equal sizes. So the shards together are going to create a cluster for this. Now, this is just, again, a container for our data to actually store them. It's a way for us to organize the data that's in memory store. And it's the key to actually having very high data retrieval, data read from Redis. So how does this work? Well, memory store for Redis clusters has what's known as one primary node that exists per shard, and they can have 0, 1, or 2 replica nodes. And replica nodes will provide high availability and have additional read throughput, and they're evenly distributed across multiple zones. Now, memory store for Redis cluster is based on open source Redis version 7.x, and this is going to support a subset of the total Redis commands that you can look them up on the Redis documentation. They go a little bit outside the scope of this video, but if you know how to use Redis on your local machine, you'll know how to use Redis on memory store. Now, there's going to be high availability with these memory Redis clusters, so shards are designed to fail independently. So connecting to them directly avoids any single failure point. So this means that reading from a data set and retrieving the shard, this high availability is built on the idea that each shard is going to be independent from one another, so there's not going to be a lot of damage. If one goes down, it will be brought back up later. So the clients are just going to do this by connecting to an individual shard network address. And then the network address is going to basically almost act as a load balancer and send the information to its relevant shards to retrieve the data. In the event that shard goes down, that just means that we're not routing traffic to that shard that's down, we're routing it to the rest. But what will happen with Redis or the memory store is that it'll bring up that shard on its own. And so direct connection avoids these intermediate hops and minimizes round trip times. And so that's the idea of using direct connection. So let's talk a little bit about replica clusters and shapes. So cluster shape is with 0 replicas per node. This is kind of what it looks like. It's just a single node. And here's what something like that will look like. So you'll have a cluster shape with 1 replica per node. So you can see I have 1 node and then its replica for it. And then a cluster shape with 2 replicas per node is going to look something like that. So this is kind of the visual representation of what these cluster shapes will be if you have 2 replicas per node. And so you can use these replicas just, again, to increase read throughput by scaling reads. Let's talk a little bit about the power of automatic failover. So within a shard, you can have failures, and these failures need to be addressed. So we'll have a failover and node repair duration. So sometimes you could have, due to maintenance or an unexpected failure of the primary node, so a failover, what's happening is a replica is going to be promoted to the primary. And you can configure replicas explicitly, but the service is just going to provision extra replicas during the internal maintenance of our downtime. And you'll have client behavior during an unplanned failover. And so this is client connections are likely to be reset depending on that nature of the failure. But after automatic recoveries, connections should be retried. And you'll want to use what's known as exponential backoff so that you're not overloading the primary and replica nodes. Now, you might have some lost writes. So during a failover resulting from an unexpected failover, acknowledged writes may be lost due to the asynchronous nature of Redis's replication protocol. So you could be writing data, the system goes down, and that data is lost for good. So client replications can leverage the Redis, what's known as wait command, to improve the data safety. And this is really the best way to handle this. So you're waiting until the system is back up to green before continuing to write the information. So you're not going to actually lose any data this way.
So memory store for Redis, here's just some recommended configurations that I would have. So you want to make sure that you create highly available multi-zone instances instead of single zone instances. We know this just from the other data stores that we use, but if they're in multi-zones, you're not going to be dependent on a single zone. So if there's a failure in that zone, you'll have a backup. And so you can actually use another data center within the same region to retrieve that. And you can create a single zone instance if you do not provision any replicas. So that's important. I recommend doing that. And then there's provision at least one replica node for every shard for high availability. And this is depending on your cost of what you're trying to do, but this is the very bare minimum. Provision at least one replica node. Ideally for highly scalable systems where serving millions of users, I'd actually raise this up to 2 replica nodes for every shard. So those are just some of the recommended configurations for memory store for Redis and how Redis works inside of Google Cloud.
So in this course, we've examined how to troubleshoot and monitor cloud environments, manage resilient streaming data pipelines, and ensure high availability across distributed systems. We did this by exploring troubleshooting and monitoring with Google Cloud Monitoring, cloud logging in the BigQuery admin panel, managing streaming pipelines for resiliency, load balancing jobs, and handling duplicate data in streaming pipelines, data replication for Cloud SQL, and high availability with memory store Redis clusters. Coming up next, in our next course, we'll move on to explore how to design and execute data migrations, leveraging cloud services, validating data, and addressing governance concerns.